Okay, I think we can get started. So good morning, everyone. My name is Amer Shalaby. I'm a professor in the Department of Civil and Mineral Engineering at the University of Toronto, and I'm also the director of the Transit Analytics Lab at U of T. So I welcome all of you to this workshop on rail analytics and simulation research at the Transit Analytics Lab. So first thing is I wish to acknowledge the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we at the University of Toronto are grateful to have the opportunity to work on this land. So the purpose of today's workshop, so the Transit Analytics Lab has been quite active since its inception in 2020 in various areas of transit domains, with a significant track dedicated to urban rail transit. So the purpose of today's workshop is to share with you some research activities and results in urban rail transit, in an effort really to stimulate discussions on research needs and priorities, and with the hope to foster some collaborations and advance our efforts to innovate in this critical area of the transport industry. So the workshop agenda for today, it's a 3.5-hour workshop. I'm going to start off after this short introduction with an introduction to the Transit Analytics Lab for those of you who are not familiar with it, and focusing a little bit more on the rail analytics research track of TAL. Then the bulk really of the workshop is going to be 2 sessions. The first will be moderated by my colleague, Dr. Brendon Hemily, on operations analytics to improve rail performance. We'll have a break after that, and then following the break, we're going to have another session on other rail-related research. That's going to be moderated by myself. And then we're going to have a discussion with an industry expert, Mr. Kenny Ling, on his thoughts and comments on the research state of the art in this area and the needs and priorities in the industry, hopefully to inform the research agenda for all researchers working in urban rail transit. And this will the workshop will end by 12:30 sharp, so we'll not keep you any further beyond that. So just a quick introduction to TAL. TAL was created in 2020, so almost in May, it's going to be 3 years, and its main purpose is really to serve as a common forum to promote transit decision-making using data analytics, and a forum really to bring together all people who are interested in this area, including transit and data science researchers, obviously transit agency and public sector practitioners, and technology specialists, as well as consultants. So this is the primary purpose of TAL, is to be that forum to engage everyone in discussions about transit decision-making using data analytics. The specific objectives of TAL, first, obviously, is to foster and advance innovations in data-driven transit analytics. Being a research unit and a research-intensive university, this is the primary mandate and purpose of TAL. The second is to foster and improve the training of students in transit data analytics. Those will be the next generation transit professionals and researchers, and this area of data science and its applications to transit is becoming a very critical one, and we're hoping to make some contribution in this regard. The third is to engage the industry, both the public sector and the private sector, in knowledge transfer and also technology transfer. We hope whatever knowledge and technology we develop at in TAL could be put to good use in the industry. And finally, a final objective of TAL is also to be involved and engaged in the development of standards and integration models, working with others, obviously, in this area. So we're actually now in an era with intensive availability of transit, all kinds of transit in big volumes and very diverse sources. So traditionally with surveys being the primary source of transit data. Those are household surveys, household travel surveys, speed and delay surveys, customer satisfaction surveys. Over and above that, transit agencies now have an abundant access to automatic vehicle location data, automatic passenger counting data, AFC data, automatic fare collection data, as well as other sources of data that's becoming also available, like mobile data in terms of Wi-Fi and location-based service data, as well as social media. There's a lot of content in social media that is related to public transit, opinions by the public and others. And network and schedule data is becoming commonly available now in the form of GTFS. So GTFS data is widely available now, as well as new and in upcoming sources of data, like for example, connected and automated technologies are promising to generate also very high volumes of data. So we are in this era of big transit data, and our approach in the Transit Analytics Lab is to utilize this data in isolation or in unison, like fusing different data, and apply advanced analytics to a wide range of applications in public transit to derive insights and solutions that are needed in the industry. So the focus of our analytics, or there are three layers of analytics that we work with. The first is descriptive analytics, which includes the computation of KPIs, and visualizing this through dashboards and maps. Second layer is predictive analytics, which are ones that are meant to provide some predictive capability, and we usually use statistical models, for example, like panel regression or time series regression or other kinds of regression models, as well as AI, artificial intelligence and machine learning methods, such as artificial neural networks and graph neural networks, and simulation. The next level of analytics that we work with are so-called prescriptive analytics, which are mostly optimization based, such as stochastic programming, dynamic programming, and also reinforcement learning, whether single agent or multi-agent. So we've been working in all those areas, and we're trying, in fact, to inform the overall transit decision making. And as we all know, transit decision making has a hierarchy to it. There is strategic planning that really usually has a planning horizon of 5 to 30 years. And this is mainly concerned with major infrastructure and modes, decisions about those. The next level, tactical planning, 1 to 10 years. This is mainly concerned about bus network structure and size, fleet sizing and technology, fare policy and technology. So making decisions about all of those. The next level is shorter term, 1 month to 1 year, which is concerned about designing route structure, service frequency and timetable setting, vehicle scheduling, crew scheduling. Then the shortest time frame is the operational management, which is usually in real time, or the day of. So schedule revisions, route management, service restoration, and rider information. So we try to develop analytics that inform the decision making at those levels, although most recently our focus has been on the service and operational planning as well as operational management. But we've also done some work in the realm of tactical planning and strategic planning. So we have several, if you wish, like verticals or tracks within TAL. Surface transit, mainly buses, and there's also on-demand transit, research in that track, multi-modal, and rail, which is obviously the focus today. So we have a significant track in rail, but just very quickly, for those who are not familiar with our work in other modes, just one slide to show you, the range of work that we've been doing on bus on-demand transit and multimodal transit within service planning and scheduling, real-time operational management, and ITS and emerging technologies. So just a few examples. Under bus, we've been working on transfer optimization, multi-depot vehicle scheduling problem, route and service design, and zero emission bus scheduling. This is an up and coming area that we are becoming more active in real-time operational and management control for buses. We've been working on AI-based control, ZEB rescheduling, absenteeism and spare board management, ITS and emerging technologies. We've done a lot of work on transit signal priority, and we're doing some ongoing work now on dynamic bus lanes and driver advisory platooning and so on. On-demand transit also has been a focus of ours recently, developing a planning framework and developing some ridership prediction models, and also aiming to develop some methods for network design. And multimodal, we've been doing some work on ridership forecasting, rider satisfaction using Twitter analytics, accessibility and equity, and so on. So our website includes a lot of information about those different topics if you are interested. And also, I invite all of you to attend our annual research day, which happens in the summer. So we will be making announcements about it for summer of 2023. But our focus today is on rail research. So in that significant track, we have three verticals, if you wish. We work on advanced analytics, simulation, and innovative operating strategies. And we work at different time frames: real-time, short-term planning, medium-term, and long-term planning. So some of those boxes, we have ongoing research or recently completed research. Some of the topics in there are actually part of our vision moving forward. So this is, what you see in front of you. This map includes really the scope of our work, both recently completed, ongoing, as well as what we intend to do in the future in advanced analytics, simulation, and innovative operating strategies. You'll get a taste today of a few studies on different areas within this framework. So I won't really go into detail into those, but you'll get a better idea throughout the rest of the workshop. Our research is conducted through partnerships mainly. So most of our projects are usually in partnership with public sector companies like transit agencies and governments, as well as the private sector, such as tech companies and consulting firms and even nonprofit organizations. And we leverage matching funding programs by the federal government and the provincial government. So this is kind of the business model of our research program. We have a range of activities within TAL. In 2020, in the first year of the inauguration of TAL, we hosted the International Symposium on Transit Data, which is an annual event that takes place every year in different cities. So in 2020, we were privileged and honored to host it at the University of Toronto. And the website the link that I'm providing here actually includes all presentations and recordings. There's a wealth of information there that I invite you to look into. Also, our website has links to workshops, annual research days, thesis presentations and papers, a lot of videos, a lot of papers. So I invite you to visit that. Our YouTube channel, as I mentioned, includes recordings of the symposium, the previous workshops, including today's workshop as well. It will be posted on our YouTube channel. Every year since 2010, we've been offering an annual professional course, actually 2 courses, one on transit planning and ITS and the other on transit modeling. And we, in fact, may introduce a course on transit analytics as well. And this is meant for professional development. So that's it. I hope you enjoyed the workshop today. And I thank you again for attending, and enjoy the workshop. Thank you very much. And now I would like to introduce my colleague and senior advisor, Dr. Brendon Hemily. So over to you, Brendon.
Thank you, Amer. So my name is Brendon Hemily. I'm a senior advisor to the Transit Analytics Lab. Been involved in public transportation and planning, operations, research for 40 years, and have a particular focus of interest on building bridges between the research and innovation communities and the transit practitioner environment. So I'm happy to be part of the TAL team and supporting their outreach, applied research, and workshops like this one. So the way this is going to be structured, the 2 sessions, the session I will moderate right now focuses on operations and simulation tools. There'll be 3 presentations that focus on some of the simulation tools and their applications that the TAL team have developed. And then there'll be a presentation on the use of some advanced analytics for planning purposes. So our first speaker will be Dr. Siva Srikukenthiran. Siva is the Chief Technology Officer at Ratio City and an advisor at the Transit Analytics Lab. He previously was a research associate at the University of Toronto Transportation Research Institute, where he managed research programs in transit simulation, schedule optimization, and travel survey data collection. The topic will be NEXUS, an agent-based simulation platform for planning and management of multimodal transit systems. Just a word about the format: we'll have the 4 presentations, all one after the other, and then if everything goes all right, we'll have 15 minutes of questions, open up the floor for questions for anyone. So Siva, please take it away. And you see your screen. Don't hear you yet, though.
All right. Yeah.
There you go.
Can you hear me now? All right. Thanks, Brendon. Yeah. So I'll be talking about NEXUS, an agent-based simulation platform for planning and management of multimodal transit systems. It's a platform that's been developed over the last decade or so to act as a bit of a nexus for simulation software and models developed by students over the years towards a large-scale network simulator of transit systems. Just a quick outline. I'll start off with the introduction around the motivation behind NEXUS and what it is, provide an overview of NEXUS and its architecture and how it works, and just end off with a brief mention of some use cases that Amer will go into in much more detail on the next presentation, followed by a quick slide on future plans. So in terms of what is NEXUS, NEXUS is a software platform combining big data stimulation and other models and analytics to support transit planning and management. And it's built on a services architecture to allow it to run across a network of computers. It was initially constructed when cloud systems were just coming into their infancy, but it was geared towards the idea of being able to simulate large-scale networks via adding more and more computational power. So the main motivation initially for NEXUS was to develop a high-fidelity simulation platform of not just the transit vehicles, but also how people might move through them and move in detail in stations with an initial application in disruption management. And so for that, we needed a system with the capability to represent the dynamic performance of individual lines. So how trains move on tracks, how crowds move through stations, but all toward how they interact at interface points on platforms to properly model the system as a whole in high detail for operations and for planning. The second capability is to provide a realistic model of passenger travel behavior under normal and irregular conditions, both at the network level, but also how agents might behave within stations themselves, and then towards being able to represent transient disruptions and emergencies and provide a platform to evaluate response strategies. So what can NEXUS do? The goal here was to allow for this to be done in an easier way. So allow user to quickly build or update a transit network model using GGFS data or other kind of data that's already been provided elsewhere. We wanted to avoid a situation you had to manually update the network, but you can leverage data that's already been exposed or provided by agencies. The second is to simulate operations and demand, so of all transit mode, rail, bus, streetcar, and pedestrian. Do so at various spatial levels. You could just model a platform or do the entire hub, or go over to the route or route corridor or network levels. And then finally, choose what was the appropriate level of resolution that needed to be modeled. So whether it's microscopic for very detailed analysis, mesoscopic, or some sort of hybrid approach. And finally, to be able to model not just the supply side, but also agent behavior under both normal conditions or scenarios of service disruption and emergencies. Now, we envisioned a few different areas for NEXUS given this kind of architecture. So first is capacity or performance analysis. So TTC, for example, just recently completed ATC for upgrading the subway lines and be able to model that ahead of time or other types of performance of operational improvements and how it might affect capacity, doing impact analysis studies, the capacity impact studies when doing large scale renovations and builds. So the most recent one in Toronto, or a large scale Union Station, testing how that might impact not just the local path network and surrounding area, but also how it might impact as a key hub operational performance across the line. The third is integrated route planning and scheduling. How do you see the impact of doing various types of alternative operations, skips off express? How do you integrate and how do you better integrate various lines to optimize transfer points? We envision NEXUS being used in these kind of work, and we have done some work in this area. And then finally, the one I mentioned at the beginning, so network resilience and response. So instead of just using simplified network models or testing what happens to you just completely take out a station, can you model shorter term disruptions? So floodings or just places where certain parts of the track aren't available for whatever reason. You do shuttle buses. How do you examine how that might impact the network, how users might respond, and then how do you model return to normal service or being able to evaluate strategies to return to normal quicker. So in terms of the overall NEXUS architecture, it's divided into a few major layers. So demand, simulation, the network builder, and data. The simulation is the place where it all kind of converges, but data feeds the demand layer to survey some of the ones that Amer mentioned in his presentation, to provide agents that go through intelligently the network and the simulation model. And then the network builder, which I mentioned, which leverages this public data to produce network models easily and act as a supply layer. So NEXUS is a simulation platform, but it's meant to be as an overall network simulator. But instead of trying to so much reinvent the wheel, we acknowledge that a lot of this work often is done in different groups with specialized software. Instead of trying to deal with one software that might compromise in any of these areas, allow users to bring in models that they have made in high fidelity for various parts, so station models, or rail models, or transit, and link them together into a coherent whole, and then overlay the agent-based framework on top of that to make it into something kind of more of the sum of their parts. NEXUS does this by connecting specialized simulators together. So those dealing with train operation, pedestrian simulation, and surface vehicle movement. NEXUS provides the mechanisms to transfer vehicles between these simulators and individuals. On top of that, provide a layer of intelligence to make agents behave more realistically or intelligently. Just like as I mentioned, done in a services-based approach, so it allows one to distribute the computation across the network of computers, and also facilitate the easy use of reuse of models that were developed for other purposes. As I mentioned, a core piece is overlaying a learning agent-based behavioral framework on top of this for transit route choice as they travel through the system. And a key piece of this is providing network awareness. So it's not just the overall network route choice that might impact the network. People do get used to, particularly for large hubs, where they might end up wanting to stand or get off. Probably the most stark example is in Young and Bloor with that T transfer that can heavily influence how a station might be used because of the and how the rest of the network might be used because of the design decisions at various stations. And finally, this can become unwieldy if you're dealing with a lot of simulators at once, and so it's essential. Sorry. The next one is to allow in simulation manipulation of transit service, to allow the simulation to be manipulated real time, and to allow the user to change train or vehicle operations, but also cause disruption and institute agents to change their behavior or respond in different ways. And then finally, because there are a lot of simulators, to provide a centralized view of it on the dashboard to be able to monitor and analyze at a network level. Now I'm going to just quickly go over one key piece, matrices, that some of you might be aware of. Matrices is a multi-agent learning based transit assignment. It's a model that was developed quite a time back by a prior doctoral student. And it basically has agents that go through a network by varying the departure time, stop and pass choices, using reinforcement learning techniques and other McCrory decision processes. And the general gist is agents go through, they try different routes in sequence, then they learn over time, and eventually they settle down on their kind of path as they try to figure out how to navigate. And this approach is being shown to provide a better and more accurate way of predicting how a population might use a network. A key part of it is being able to reroute midway, given based on new information, which is particularly important when you want to test transient disruptions or other kind of momentary changes in service. The goal for NEXUS is to integrate matrices as these agent frameworks. It's still ongoing work to provide the intelligence overall for the system, and act as a point where we can add in and improve the behavioral model over time. Now it's going to just quickly go over some use cases. This was the original prototype way about a decade ago at this point of the TGC network. The key thing is being able to, again, these are a whole bunch of simulators running at once under the hood, and Amer will show a video of this, is Bloor and Young built at high detail, where you're able to utilize that model in conjunction with the rest of the network to get a more holistic evaluation of capacity and movements. There's a bunch of other previous studies. So under capacity analysis and flow management, a USRC study under various sort of service operation changes, crowding relief benefit of the DRL, crowding analysis of Bloor Young, rail disruption management, hub and network flow management, and then a few other kind of one-off projects in specialized route operations, transfer optimization, and integrating it with an activity-based demand model. So finally, for the future, as I mentioned, this NEXUS was built on the services-based architecture, but it does need an update to use some of the more recent advancements in cloud services. That's one thing we are looking to provide, which is a web-accessible version of NEXUS. There have been advancements in reinforcement learning over the years, and the latches is undergoing an update, at which point we'll be looking to incorporate that. And there are some mesoscopic station and rail simulators that are being developed by TAL. We'll hear about them today, which will also be integrated within NEXUS. So that's all I have. So Brendon, back to you.
Thank you, Siva. That's a great overview. I know it's a lot of information to put into a very short amount of time to provide an overview of the whole web of different simulators of NEXUS. For questions, there's two options. People can insert questions into the chat room, and Willem is monitoring those, or you can raise your hand, and then we will let you unmute yourself to actually ask a question verbally. But as we mentioned, we'll continue on and get all 4 presentations, and then we'll open it up. Hopefully I'll have a nice time for questions. So our next presenter in this sequence is Amer, and he's going to follow up on Siva's presentation to actually delve into a bit more detail about some of the sample use cases. So Amer, take it away.
Yeah. Thank you, Brendon. So yeah, as Brendon mentioned, I'm gonna share with you a few sample use cases. I'm gonna start off with the slide that Siva showed. So as he mentioned, NEXUS has been used in a number of previous studies. Those are grouped in 2 categories. The first is capacity analysis and flow management. I'm going to share with you results of those highlighted boxes, capacity analysis of the Union Station rail corridor. For those of you who are not from Toronto, Union Station is the biggest transit hub in the city and in Canada, in fact. And the rail corridor is, it's actually connecting 7 rail lines, commuter rail lines. We've done a capacity analysis using NEXUS of that corridor. The second study I'm going to share with you is on Bloor and Yonge Station in Toronto. Again, it's one of the busiest stations in our subway system, and before the pandemic was overcrowded, and even now, you know, high volumes are recovering, and so we also conducted a study using NEXUS on crowding and crowding mitigation measures in that station using NEXUS. Then I'm going to talk about hub and network flow management. So there's an ongoing work right now by a PhD student trying to develop some methods of managing both the crowd flows and the vehicle flows in multimodal hubs. We're using, again, Union Station and the downtown network as our case study. And I'm also going to share with you some work on rail disruption management strategies that we also built on top of NEXUS. There have been other research studies, like specialized route operations, such as skip stop and zonal and express and so on, that we also use NEXUS for, as well as transfer optimization. As was mentioned in the chat, there is pretty much we have a paper on each one of those studies, of course, the ones that are completed. And if you are interested, we would be very happy to share those with you. So starting off with the first one, capacity analysis of the Union Station rail corridor. As many of you know, that the Union Station was underwent major reconstruction over the past decade or so. One big question was really, what is the capacity of Union Station and the entire corridor that actually it's sitting in the center of? We used NEXUS to develop a simulation model of that complex system. So what you see on the top left is a rail simulation model of Union Station, and as you can see, you have all the platforms here, and to the east of it, there's the track infrastructure and the interchange or ladder system, and there's a similar ladder system to the west of the station. And then we have multiple lines. We model up to 1 station away. That's really the definition of the Union Station rail corridor. and simultaneously and within the same framework and in an integrated fashion within NEXUS, we developed also a model in the crowd movements and crowd flows and densities on the platforms and how they interact with the train movements. So this is the model that you see at the bottom here. This is a mass motion model that's integrated with the open track model. And we did a major study. We collected data, calibrated models, and we conducted the capacity analysis, essentially a stress test of the station to see how many trains per hour that the station can handle within the morning peak period, which is mostly inbound traffic. So trains are coming from suburban areas into Union Station. And we did what you see here is one result from the study that looked at the on-time performance of the trains. And we found that beyond 39 trains per hour in the morning peak period, and those are inbound trains, the level of service in terms of simulated on-time performance starts to decline quickly, which we used to, or this is the conclusion that we reached, that the capacity of Union Station, and that of course was before the major reconstruction that took place. One of the big issues really there was narrow platforms and stairways into the concourse level, and that interaction between the high densities and flows of crowds on the platforms with the trains actually created some constraint on the capacity of the station as a whole, of how many trains it can handle per hour. And this is very clear here in the heat maps that you see in front of you, where really the hotspots are mainly at the stairway entrances, so stairways from the platform level to the concourse level. So the interaction between the dynamics there and the train and dwell time caused or presented a major constraint. The next study was focused on Bloor and Young station. And again, Bloor and Young is one of the heaviest used stations in our subway system. It's an interchange station. So there are the two lines, line 1 and line 2, intersect there, and there's a lot of transfer movements. So the two lines are at different levels. So passengers transferring from one line to the other, they have to go either upstairs or downstairs. And the morning peak period, there's very, very heavy flows, transfer flows, and also incoming and terminating flows as well, that all really interact with each other. So we wanted to explore first really the patterns of crowding and congestion there using NEXUS, and mainly focusing on the crowd simulation part of it, mass motion. So what I showed you here is the simulation of that, but we used that simulation to produce a number of scenarios to look at, how the train arrival patterns. So remember, we have two lines. So we have line number 1, we have northbound trains, southbound trains, and line number 2, eastbound and westbound. So we wanted to explore the arrival patterns and how they impact system congestion. So what you see in front of you here is an output of NEXUS that shows using the eastbound trains as a reference and looking at different offset levels. So offset levels for the westbound trains and the north-south trains. And what we found interestingly here, or as in summary, that the best arrival pattern is when trains are kind of staggered. So again, to give you an idea that the headway on those lines is about 2.5 minutes at the time of this analysis. So we found that the best train arrival pattern that minimized the average passenger congestion. So average passenger congestion is really the average time each passenger spends in level of service F, which is highly overcrowded. So we found that that time is minimized when trains arrive in a staggered fashion with a 1 minute offset from each other, roughly speaking. And expectedly, the worst case scenario is when trains arrive more or less around the same time with an offset of 0 or 2 minutes, meaning, you know, very close to the next train. So you see here that the values actually vary by about 40%. So under best case scenario, when trains are kind of staggered, if there is a way to stagger the arrival of trains at that station, you can minimize or you can reduce the amount of time each and every passenger on average spend in level of service F versus if they come more or less around the same time. We used those two best and worst case scenarios, and we looked at if in fact they can even be what's the impact of ATC, automated train control, which is now in full operation on line number 1. Also looking at another strategy of trying to distribute the passenger demand on the southbound platform, which is the heaviest platform in the morning peak, to have it in a passenger demand or passengers to be distributed uniformly on that. And we found that we can, for the best case scenario here, which you see when the trains arrive in a staggered fashion, you know, 1 minute between trains on different platforms, we can even further reduce that amount of time in level of service F per passenger to further reduce using ATC and using also passenger flow distribution along the platform. So this is this gives you an idea of really the capabilities of NEXUS in modeling those complex settings. There's an ongoing study right now to look at the network level, how we can in fact try to manage the flows and control the flows of both passengers and trains in a way to minimize overcrowding and to prevent overcrowding from happening. Because we know once overcrowding occurs, it can exacerbate the dwell time and it can reduce the practical capacity of the track infrastructure. The train of the trunk lines. So for this, of course, you know, microscopic simulation is a bit of a challenge. So we're currently developing sort of a mesoscopic or / macroscopic both crowd simulation model using something called CTM, cellular transmission method, and simultaneously developing also a mesoscopic model for railway operation called Spur. And there is one presentation after mine that's going to talk about this, and also building some capability of reinforcement learning based control. So we build a reinforcement learning agent and train that agent within NEXUS, within the simulation platform, to come up with the optimal control policy with respect to, you know, how many passengers should be allowed into a particular platform, and also some kind of control policies for the train movements as well. So it's based on reinforcement learning, but this reinforcement learning is taking place, or the training of the reinforcement learning agents are taking place within NEXUS, the NEXUS simulation platform. This is sort of an architecture of the solution that we are envisioning. So the model-based reinforcement learning station control is trained within NEXUS, and it interacts with the railway station model and the crowd simulation model within NEXUS. And so we don't have results of this yet, but I thought of informing all of you about this ongoing work, and this is can only be was only enabled really by NEXUS. Otherwise it would be hard. One of the key inputs into this model is, because this is meant really for real-time control, is the ability to predict origin destination flows in real time. So we are again currently by the same PhD student, he's trying to develop prediction models using graph neural networks of OD flows. So you can think of this model after its full development, it will be able to predict the OD flows over the next, let's say, 15 minutes using current available data. And we're trying to utilize Wi-Fi data, which is currently available in our subway system, and we have access to it here. And we're going to talk about some of the other work that's utilizing Wi-Fi later in the workshop. Okay, so the last thing I want to share with you is on rail disruption management, specifically on bus bridging strategy. So as you know, and probably many of us have experienced this, when there is subway disruption in Toronto or in other places, so a segment of the subway is closed, the transit agency dispatches buses from different bus routes to serve as shuttle service to serve the passengers who do not have subway service on that disrupted segment. So a big question is and this strategy is called bus bridging. So a big question is, how many buses should be pulled from different regular routes, and where those buses should come from, which routes they should be pulled from. So we developed a capability within NEXUS that enables transit agencies and dispatchers to test different bus bridging scenarios in real time and see the impact of that. So we built something called Dash Bus Planner. So the user, and I'm going to show you, we have some dashboard for it as well. So there is the user or the transit dispatcher inputs like the incident location and time. And this is, again, remember, in real time. This is meant to be used in real time. Also enters the expected duration of the incident, the dispatch time and demand reduction, how many people are expected to leave subway and, walk or take a taxi or Uber or whatnot. And also number and assignment of shuttle buses. So the user here, the dispatcher, enters the number of shuttle buses and where they should come from. And then the Dash Bus Planner, which is a module within NEXUS, using some simulation model of the crowd dynamics and also the bus dispatching, it computes a number of metrics on the impact of that bus bridging scenario on this subway passenger delay, the bus riders delay, those bus routes from which the buses are pulled to serve as shuttle service, they obviously would be impacted. So we produce, the impact in terms of the delay inflicted on bus riders of those routes and a number of other metrics. This is one version of this bus bridging toolkit. Another one is what we call Dash Bus Optimizer. So this one, in fact, optimizes for the user. It determines for the user what is the optimal number of shuttle buses that should be dispatched to a particular incident with some given characteristics, where it is, and the expected duration of that incident, and so on, and the time of the incident. And it decides for the user, the optimal number of shuttle buses and also the assignment where those buses should come from to minimize the total delay for both subway passengers as well as bus passengers. And so it determines the number of shuttle buses, the optimal bus routes, where those buses should come from, and the number of buses from each route. And it computes, again, a number of metrics. So this is a module that was built within NEXUS that utilizes some of the capabilities of NEXUS as well. And it's meant for rail disruption management. There's a graphic user interface for it that we also built within NEXUS that allows the user to enter all the incident information and if they prefer certain routes from which to pull buses. Then the output is shown on the right here. It shows a map of, this is the incident, which is, the red dots here, subway incident, and the colored routes here are the routes from which buses will be pulled to serve as dispatch, to serve as shuttle service. So I hope this gives you an idea of the two presentations by Siva and myself about NEXUS, what it is and how it's built and what it's capable of, and some of the use cases that we're that were implemented and performed using NEXUS. So that's it. Thank you very much.
Thank you, Amer. Like we said before, we'll hold the questions. I see some people have been putting questions into the chat room. That's great. And then when we get to the opening up, we'll also take live questions by unmuting people. Okay, so that our next, I think that gives you a pretty comprehensive view of NEXUS and some of its applications. Our next presenter, Peter Lai. Peter is a fourth-year undergraduate student in engineering science, specializing in electrical and computer engineering. He has an interdisciplinary interest in designing and developing innovative and intelligent technology systems to power public transit operations and planning. His work includes Spur, a mesoscopic simulator for stochastic railway networks, and that's what he's going to present to us. Thank you, Peter.
All right, thank you, Brendon.
Can hear you, can see you.
Great, awesome. All right. Hello, everyone. My name is Peter, and as per Brendon's introduction, I'm a fourth-year undergrad student in engineering science at U of T. And as part of my undergraduate thesis that's ongoing currently, I'm working with Willem and Amer on the Spur project, which is what I'll be presenting today. So as the title says, Spur, or the full name, Simulation for Planning and Understanding Railways. It's a modular, data-driven mesoscopic simulator for stochastic railway networks. So there's a lot of keywords to unpack here. Let's start with perhaps the most important part, which is the what and the why of mesoscopic railway simulations. So many of you here will be familiar with OpenTrack, which is a popular commercial railway simulation software that is classified as microscopic. And predominantly microscopic simulations are used in research and industry. And the main benefit of microscopic simulations is the high level of detail and accuracy. So we can achieve the most realism by including detailed information about the physical infrastructure, the signaling system, vehicle physics, operational data, and so on. However, all of that detail has a cost, mainly the long computation times and the complex setups and the large data requirements, which makes it unsuitable for analysis at the network level. And it's hard to be applied in a real-time context also. So as an example, in our previous discussions on NEXUS, we saw that much of the current work so far has mostly focused on microscopic simulators with mass motion and OpenTrack integrated together. And that is not really appropriate for any larger scale applications because the computational times will be a lot higher. On the other side, we have macroscopic models, which are also traditionally used in rail modeling. And they're like the opposite of microscopic models, where the network representation is very much abstracted. So we can get results really fast, but those results are limited to higher level aggregate stats about network level performance. So you can't really easily capture things like delay propagation, for example. So between the traditional micro and macro simulation models, we see trade-offs in speed and granularity. So this is where mesoscopic simulations come in to bridge the gap and combine the best of both worlds. So the idea is that depending on what's relevant for the specific context of the simulation, we can represent certain aspects of the network at finer granularity while abstracting away other less relevant parts to save on the computational time. So this will give us useful results quickly without needing a whole lot of overhead in the model building process. And that is what lets us scale. So here's a chart that kind of just goes into the comparison between micro and mesoscopic models in more detail. I've kind of touched on some of this in my previous slide already, but the general idea is that we're representing the network in nodes and edges in a graph format. We're using simplified control logic, and we're not really calculating things like the physical motion equations of the train dynamics, and we're not thinking about traction and resistances. So that means we can really model things at a bigger scale and get results faster as well. And we only need network level data. So mesoscopic simulations make it much more feasible to do rapid prototyping, for example, and perhaps be applied in a real-time context. So what has already been done in terms of mesoscopic simulations for the rail domain? So they have been used to model traffic flow in general in the road context, but there are limited works in literature where they were applied to the railway context. So here's a list of some of those works. And we can see that they're largely fragmented. So a lot of them are specialized pieces of software. They were applied in a limited scope, so not all of them were at the network level. They're not all supporting stochasticity, which is very important to model real-world operations. And also they're all in proprietary setups, which means they're difficult to access. So this presents a gap where today there's no existing mesoscopic model that is a universal flexible piece of software that could be easily modified or extended to suit different railway simulation contexts. So that is where Spur comes in. So Spur is a flexible mesoscopic railway simulation platform for rapid prototyping, simulation, and analysis. So it has all the key attributes of mesoscopic simulations we've talked about just now, and fills the gap in the literature in this area. So specifically, Spur is modular, which means the various components could be quickly switched in and out. And I guess the picture of that will become clearer when we get to the architecture later on. Spur is agent-based, so we're tracking individual vehicles, which makes things like delay propagation a lot easier to do. Spur is event-based, so the simulation runs chronologically, and they're driven by discrete events. So we skip the time steps where there is no change and only update the components that are changed, which saves on computational time. Spur is stochastic, so we capture the randomness that is inherent to real-world operations. Spur is data-driven, so the components will be parameterized and calibrated using real-world data. It will have a graphical user interface, so we can quickly build models and easily build them as well. And finally, Spur is open source, so anyone could access it, use it, and contribute to it. So use cases and applications. So Spur is really intended to be used to look at the big picture. And the key idea is that you can quickly get results at the network scale without having to spend too much time or money. And this enables things like rapid prototyping we mentioned earlier, where it becomes sort of like a playground for experimenting with outside the box ideas, which might be useful in situations like planning a new service. So some of the applications include network capacity analysis, simulation-driven optimization. So in terms of timetables, routing, or control algorithms, things like disruption management, and also finally integration with pedestrian flow simulations and surface level surface transit simulations, such as through NEXUS that we just talked about. So Spur can work both as a standalone software and also as a module to be integrated within a meso or macroscopic version of NEXUS. And it'll talk to it through an API or something along those lines. Okay, so now let's talk about the architecture of Spur. So this is kind of like a logical flow diagram where we have a model controller, which is like the brain of the simulation. It holds the network structure in the form of a graph. So with that, it can do things like routing. Each edge of the graph represents a component. So the components, they could be abstracted to whatever level of detail. It could be a very short section of track. It could be a very long section of track that is hundreds of kilometers long. There's lots of flexibility there. Trains follow a sequence of routes, and at each route segment, they ask the component to use or occupy it, and the component decides how long to hold the train. So, and this process basically repeats throughout the timeline of the simulation. So here is a organizational hierarchy of the various entities in Spur. So as we said, the model is the brain. It has the graph representation of the network, which has the nodes and edges, and there are the various components in the network. And each root is encoded as a sequence of physical segments, each of which is one component. And then each train follows a sequence of routes, which we call a tour. And you can think of it like a service block in transit operations terms. Multiple routes can share the same components, and routes can also be reused among tours, because a tour is a sequence of routes. And so the modular design of Spur really makes it easy to swap different things in and out. So you can swap out components, you can change the route, for example, and observe the effects. And the event-based simulation, the event-based nature of the simulation means we can pause the simulation in the middle and change some things like modifying the route or the tour, and then resume the simulation and observe the effects. So here is another, I guess, like a showcase of the modular nature of Spur. So we have components, we have various different types of components. They have the same interfaces, so we can connect them up like Lego blocks, so to speak. And we can even build custom components as needed. And we also have jitter, which is what models stochasticity in Spur. So it perturbs certain parameters, a common one being the dwell time or travel time. And it could be a fixed value, it could come from a random distribution, and there's flexibility in the different types of distributions we can use for it. So the modular design really enables the interchangeability of components and jitter types. So for example, if we want Gaussian jitter, but then we want to swap it out with the log normal jitter, we can do that very easily. So that is that interchangeability is one of the main benefits of Spur. Okay, so now I'm going to go through a very simple example of the TDC Shepherd line built in Spur. As you can see, it's a very simple network, only 5 stations, and we're only using parallel tracks. So some simplifications were done where, for the line section between 2 stations, we're viewing them as one single track segment. There's no crossovers or anything like that. But the idea is that the network representation has that flexibility of being more aggregate or detailed, and that is fully up to the user. So for the schedule, we're importing that from the GTFS static feed, and we can use it to set specific departure or arrival times at certain stations for the trains. So in terms of results, we're getting these stringline diagrams where you can see first we can model the normal operations as scheduled, and then we're also adding a little bit of jitter. So in the top diagram here, we're adding just a very small amount of jitter, and at the bottom we have a very big delay. So in both cases, you can see the propagation of the delays. So the trains are waiting, they're following each other without overlapping each other, and all of this is based on the very simple rules that we set in the components, such as each track segment only allowing one train at a time. So that whole thing plays out throughout the timeline of the simulation. So lastly, I'm going to give a brief overview of the ongoing and future work for Spur. So in the short term, we're looking to simulate the entire Go network, the Go train network in Spur. So that will involve building a bunch of new components. So that includes, station components of like varying complexity, from the single platform ones to larger hubs like Union Station. the ladder structures, east and west of Union Station and all of that. We are looking to use real operating data for calibration and validation. And we also want to automate and standardize the GTFS import process so we can set schedules easier and also build these input files to a simulation in a more automated way. I'm just going to jump ahead here and show like a very conceptual example of what the Go network representation in Spur might look like. So this is all based on information in the track diagrams, and this is specifically the Go subdivision, on the eastern portion of the Lakeshore East Line. So each station here is represented in components. We have some representations of the track segments and crossovers and things like that. So all of this is in an abstracted package. So jumping back, in the medium to long term, we're looking to build a full graphical user interface for model construction. So it's going to be like a drag and drop style, where we can quickly build the components and assemble the simulation scenarios using a mouse. And we're also looking to have a central controller for automatic reroutings and more complex dispatching tasks in general. And there's a lot of other possibilities. So this is a continuously evolving project that is very much open. So I will end by plugging the GitHub link of the project again. Again, it's open source, so feel free to check it out. And we welcome contributions and comments. And yeah, I'll leave it there. Thank you.
Thank you, Peter. A lot of information. As we've said before, we will let everyone know all the presentations will be available after the fact, and I believe the recordings as well, and we'll let everyone know about those. So having had 3 presentations about sort of the simulation frameworks and their applications, we have a 4th presentation that's looking more into the use of advanced analytics for planning purposes. So Willem Klumpenhouwer, and he's going to talk about using delay logs and machine learning to support passenger railway operations. So Willem is a postdoctoral fellow at the University of Toronto's Transanalytic Lab. His research finds innovative and expressive ways to evaluate the performance and design of transit systems and provide insights to planners, operators, and advocates about how useful, reliable, and equitable their transportation systems are. And again, as he goes along, be sure to put questions in the chat room. Willem, it's all yours.
Thanks, Brendan. Hi, everybody. My name's Willem. As Brendan just said, I'm a postdoc at TAL here. And I'm going to talk to you today about a project that Amer and I did with collaboration with Metrolinx, with some data sharing agreements with Metrolinx, to really dig into sort of an example of digging into a specific type of data set and trying to learn sort of how much information we can squeeze out of it and sort of get this first blush idea of how we might be able to use this type of data set to help with planning and analytics in the future. So we're talking about a data set called, I'm going to refer to as delay logs. Most rail operators and Go Transit is no exception, maintain a log of when there are delays on the network. This is sort of a stylized version of what that data set might look like, but basically there's columns for various attributes of when there's a delay. A delay is recorded whenever there's 5 minutes of delay or more in a specific incident. Often there'll be delays that are shorter that are also recorded. So we have a pretty rich data set of all the delays that have occurred on the network. And we got 5 years worth of data to look at as well. And so that opened up the possibility to do a little bit of machine learning and things like that. But attributes included, time, of course, and location and the delay length. And then there was a sort of a business unit who was responsible for the delay in one way or another. And that could be a little bit recategorized based on what we were looking at. And then finally, there's sort of a free text description that happens at the end of the delay log, where the dispatcher can type in a little bit more details, a little bit more free flowy about what's happening. And so we use that also a little bit to gain a bit of insight. So we'll dig into that. I also wanted to just sort of refresh you of what the Go network what the Go network looks like. Here's sort of a map of the whole network. As you can see, there's a couple of key points that I've added that you'll see pop up in the presentation. So for example, around Union Station, there's a couple of key locations which are not stations, but are key switch points and interlockings that show up in some of the delay analysis as well. So we wanted to learn a little bit about like where delays are occurring on the railway network, some summary statistics, learning about kind of what delays are most common or largest. We wanted to learn a little bit about if there's, connections between locations on the network in terms of delays. We wanted to look and see if we could provide historical context, so a little bit of operational support to provide historical context to users and also to make predictions about emerging incidents. So ultimately to see if we can try and support operations by providing a bit of additional information and nuance as well. So this is sort of the research paper in a graph. We have so you can see there's some data cleaning. There's in orange here or in yellow where you can see the main sort of outputs. Topic modeling we'll get into with some of those free text things, as well as topic and theme grouping. So we manually translated sort of some of the conversation about business units or who was responsible for the delay into some of the root causes. So a broken switch might be a maintenance problem, but ultimately it's a broken switch problem from a sort of larger picture view as well. And then on the bottom we have 4 different outputs that we provided also in the paper, and we'll go through each of those as well. So 2015 to 2019, we had about 70,000 delay, almost 71,000 delay records. We sort of summarized them into what I called themes, which are very much large themes in terms of delay. And then, themes are made up of a series of topics. So on the right side of this slide, you can see the most common or the highest average yearly delay by topic on here. So on average, priority to any sort of situation in which a train was given priority over the train that was delayed. So it could be a Via Rail train, it could be a freight train, it could be another GO train that obviously caused the most delays. And then large disruptions such as signal failures and construction also played a role. We also looked at sort of how long a given delay would sort of last, and we can see that safety and track and way problems and weather problems kind of induce the highest amount of delays or the highest individual delay length. But due to the frequency of them, sort of people-train interactions, which can include vandalism, it can include incursion onto the tracks, things like that. Those kinds of things provided a high amount of delay as well. I just want to go back now to this free text concept. So this is a sort of anonymized example of what this free text looked like. So as an event unfolds, if there's an event that's sort of surrounding the same thing that's happening, so let's say there's a broken train or a train that is running slow, or there's some crowding and the same train gets delayed multiple times, those free text boxes get extended for each delay log. And so we're able to link together these events that are happening into sort of a larger incident. And from that, we can sort of make some connections between, events that happen together as well. Similarly, for example, if there's a broken switch on the rail network, that may affect multiple trains. Those things will be connected too, because the method in which the text is recorded lets us sort of stitch together these events. But you can see sort of a sequence of events here happening due to late arrivals of trains. And so we wanted to know, how those things are connected. So one sort of machine learning thing we can do is to use topic modeling. So if we take that free text and we really pull out the key words or the key sort of root words of things, and we remove some of the superfluous words, we can do short text topic modeling. Effectively, that lets us sort of find common groups, common clusters of words, and then look at how often those clusters appear within these different logs. And so what you see in the table below here is the top 5 groups of 5 words. So along the rows are 5 words that are clustered together by the algorithm. And then you can see, the 5 rows are the top 5 of them. So the top one, overshoot, platform, reverse, required, foot. We can see that that's a topic that's talking about a train who overshoots the platform and has to reverse. Usually they talk about how far they are, how many feet they're past. You know, in the middle, we can see via late wait follow train. This is a common thing that happens where a GO train might be stuck behind a late via train coming in, for example, from Montreal, and is following that and has caused delay. So even without this sort of classification system that was provided by Metrolinx, we are also able to sort of determine some categories outside of that as well if we wanted to. So I talked about sort of stitching these events together into incidents. So basically, whenever there's two locations that are part of the same delay, you can think of us as sort of drawing a line between them when that happens. And if we do that for enough delays, we can build a graph, a mathematical graph, and then we can look at the graph and sort of see how strong the connections are, how much delay is shared between locations, and see if there's key locations in different ways that are a part of these things. So for example, in the top, we're just looking at pairs of locations that are sharing the average delay. So we can see the two ends of the Lakeshore East and the Lakeshore West line are in common. So if there's an incident that happens throughout the line, it likely will affect Union Station as well as the terminus station on the other end. And then we can do other graph theory things like looking at how much a node influences other nodes. So obviously Union Station, it being the center of the network, you know, is a key location. If there's delays there, it tends to cause us delays elsewhere, as you can imagine. Similarly with the high frequency or the higher service lines along the lakeshore as well. And then we can also look at places that act as a bridge between others. So are there places where they tend to sort of connect delays from one side to the other? So they're kind of in the middle of things. That's called betweenness. Believe it or not. And so there you get locations that are not necessarily stations where you can see that, you know, issues in between. You may have issues that sort of run along this Union Station corridor, and I'll just bring that map back up for you. So Bathurst Break was mentioned there, and you can see that's all around that Union Station rail corridor. Another thing we can do is use this historical information. So I used to work briefly as a rail dispatcher, and I know that, you know, when incidents happen, you're a little bit at the mercy of your own historical information. And so the idea was to say, can we find, you know, very quickly, given an initial condition of an event happening? So we know there's a signal failure at Oshawa, and the weather is good and the temperature is normal and it's in the morning. Can we look up other incidents that happened at the same time or with similar characteristics and provide those quickly to a dispatcher so that they can look at how they were resolved in the past and maybe either make the same decisions or better decisions if things didn't go well. And so we used what I call the historical incident, you know, recommender, and it uses sort of the same algorithm, similarity algorithms that Netflix does, for example, to recommend movies to you based on what you seem to like. And so it matches up events that match as well. And finally, we wanted to do a little bit of regression or a little bit of machine learning to see if we could learn a little bit about both whether we can predict how long a delay is going to be a little bit better than you might be able to predict just with your gut or with using the average, as well as to learn a little bit of some of the factors that were influencing the prediction as well. So can kind of understand what factors are pushing the delay higher or lower when we make these predictions. We used two different prediction methods. So we used random forest regression, which is the chart on the left we'll talk about, and then we used elastic net prediction, which is the chart on the right as well. And both of those were able to make predictions that met performance metrics that were a little better than you would be able to do as if you were just stuck with the initial delay and you didn't add any, or if you just took the average for the data set, which may seem very straightforward, but in my experience is a little bit the sort of information you have as a dispatcher in some cases. So we can do a little bit better with prediction methods in terms of how long the overall delay is going to be, and hopefully that can be used to communicate out to users. But the interesting thing, we'll focus on the top right chart to see the sort of the major factors that influence the way the model makes predictions. And you can see at the top, so the orange colors are topics and the blue colors are locations of delay. The top three are pretty clear. So if there's a fatality or a near miss, obviously that's going to push the predicted delay up significantly. Same with rule violations and safety violations, and same with switch and signal failures, track failures, obviously push those delays up. So the model is making predictions, using a certain amount of logic there that I think matches with experience. And then obviously the initial delay is a big factor, because if a train is delayed for 5 minutes, it can't be delayed for less than 5 minutes. So that's an interesting way to push it. So, and then we can also use it to identify some locations that are perhaps causing larger delays than others. And that might be we might be able to look at those locations to see if there's something you can do, some intervention you can make so that they don't influence those quite as much. So for future work, so this was sort of a first blush of like, how do you take this data set and get as much information out of it as possible. Some of the predictions and some of the things we'd like to do are to combine these delay logs and some more location-based data to see if we can get sort of corridor-specific predictions or a little bit more fine-grained, nuanced predictions, so that when something happens on a corridor, we can adjust for that. Looking at sort of delay propagation, so probably connecting this with something like Spur to be able to understand and do some predictions based on how delays might propagate throughout the network and provide that information as well. Using some of these historical incidents to perhaps simulate and run response scenarios and do some scenario planning. It's a common practice as well to do some sort of games or scenario planning so that you can respond to these in a sort of set way. And also maybe doing some of this simulation on the fly, keeping track of what's going on, and provide some prescriptive methods as well, and to use it to look at realistic disruptions. So thank you very much. Thank you very much to Metrolinx. We had a great agreement with them. We were able to share data with them, and it was wonderful to be able to work with this data set.
Thank you, Willem. That was great. Totally different, but really interesting. So we have 15 minutes for questions. There are already a couple specific questions in the chat. I'm going to pick first for Amer or Siva, the application to the Bloor-Young. There was a question there about I guess the holding the trains so that they don't all arrive at the same time. Has there been any further analysis of that, or is it, and its feasibility, I guess, too? And are you muted or no? You okay?
I'm okay. Yeah.
Okay. Good.
Well, yeah. Thanks, Jeremy. I think a very good question. That study, when we did it, obviously was only focused on Bloor-Young station. We just wanted to see really the arrival patterns and how they impact crowding within the station itself. The current work that I referred to about hub and flow management using reinforcement learning looks really at the network as a whole. Obviously, we cannot just hold trains, and as you pointed out, this might in fact really have some negative impacts on or cascading impacts on other parts of the network. So the current work is taking a wider perspective now at the network level to look at how we can actually manage flows of trains and passengers at individual stations, but also taking into consideration the network performance as a whole. So stay tuned for that.
Okay, thank you. There's a question that dovetails a question of mine for Peter from Kathy. It has to do with the concept of jitter events or the stochastic aspects. Could you just spend a minute first to explain the different categories of jitter that you just quickly flashed on one of your slides? And then Kathy's asking whether it's best to just choose one or test them all to see how they might change the outcomes.
Yep, for sure. Can you see my screen?
Yeah, but it was
Okay.
a couple slides before that, I think.
There we go.
It is, yeah.
So the idea with jitter is that it's random factors that may influence the operations along the network. So this is just a few examples of the possible kinds of jitter that we have. So, and a lot of these are, probability distributions. So it's basically at any specific instance in the simulation, it will be a random value from these probability distributions. And also, I think the disruption jitter is, I guess, like a length of time where service is interrupted. And Willem, feel free to jump in as well about that. But the idea with Spur is that because of the data-driven nature, you can use real-world operating data. So perhaps you have delay logs like Willem just talked about. You can use that and fit your own distribution functions to those data. So you can get a more accurate, you can capture the delays more accurately and put that into your simulation. And you can also, because it's modular, so you can use it as sort of a sandbox. You can experiment with jitter at different parts of the network to simulate it. You can use real world delay logs to identify different bottleneck areas of the network, and you can apply jitter there just to observe all the effects. So you can really do like whatever you like with jitter based on your own simulation context and some real world data on delays and dwell times, things like that.
Yeah, maybe
Okay.
I'll just add a brief bit of context there. So I was a physicist by training originally, so I think in terms of perturbation theory. So you take something and then you kind of knock it around, and that's sort of what the jitter is supposed to be about. And in terms of data, right, it really depends on how much data you have. If you have enough data that you can sample directly and create your own distribution, that definitely is a possibility. If you don't, you may need to sort of take the parameters like the mean and the standard deviation and decide it's Gaussian or decide it's something else, and use that to sort of train. So it's still data driven, but you're sort of making some trade-offs in terms of how much data you have and the theory you can kind of do. And then there may be some practical things you want to do, like Peter said, where you just want to have the train stop for 20 minutes because something broke, or you want to insert a specific incident. Then you can use that as well. So, and of course, you can always write your own as well. So the idea being that you can really customize it if you need to.
Yeah, and I guess if you have enough data, you can actually see which kinds of disruptions correspond to which kinds of distributions of stochastic.
Exactly. But if if you're going with something new, you can set a default and say we think it's roughly this and go from that.
Okay, great. Willem, a couple specific questions there too. One having to do with whether one could use this approach to announce typical patterns of delay, so that this kinds of disruption is this much of a delay. And the second question is how standardized, if I understand correctly, how standardized are the recording? I mean, you worked as as a railroad dispatcher. Is it a bit free flowing that people put whatever they think is the right word, or are there pretty good standard operating procedures?
Yeah, I mean, I can speak only for my experience, in the past as working at CP Rail and what we did at CP Rail and what I saw in the Metrolinx data. Both of them are structured data for the most part. So there are attribute columns, there's timestamps. When I worked at CP Rail, it was so busy that often you wouldn't get to your delays until after your shift was over. And so, your memory of what happened might be a little bit fuzzier. And it was a separate, ironically called NEXUS, a separate piece of software that also where you would sort of update these delays from a customer facing perspective. So they weren't quite as connected to the operations. So how standardized it is, I'm not sure, but I have seen other research working with other delay logs that were also able to sort of dig into some of this free text and do some auto categorization. So I would imagine that each company sort of develops their own lexicon, develops their own sort of standard way of doing it, and that gets trained into people. So you would likely, when you approach a specific company, you'd likely be able to sort of adapt what you're doing to that. And the topic modeling would do that automatically, I think also.
Mm-hmm.
Like there's examples, like there's also specific location and things, examples like there's a drawbridge on the over the canal near St. Catharines. That's something that has language that's specifically about that, and they don't specifically mention the drawbridge. They use the seaway, right? And seaway doesn't show up particularly elsewhere.
And the question about whether you could use this to sort of provide passengers with information about typical delay times.
Yeah, I think that would be useful. I think you'd have to sort of dig in a little bit more specifically about what line you're on, and perhaps and what, you know, how, and maybe combine it with a bit of simulation. But I do think it'd be super useful to be able to say, like, typically that this takes, you know, 20 to 30 minutes to resolve versus typically this takes, you know, 5 to 10 minutes to resolve, and people can start to make decisions based on that. And you can, you know, there's ways to figure out the language to communicate that, you know, you have some uncertainty, but not too much uncertainty. And I think that would be really useful. Yeah.
No, the passengers really have a lot of problem when there's total uncertainty about how long it's going to last,
yeah,
whether it's 5 minutes or whether it's 2 hours.
Orders of magnitude already are helpful, right? So
yeah. I would think so. Question for Siva. On your last slide, you talked about the future. In particular, the improving, enhancing the cloud-based for format, as well as the integration. I assume the cloud-based would improve computational time, but could you maybe just elaborate a little bit more now that we've seen the other presentations? Siva, are you there?
Yeah, I'm afraid I think Siva had
to run. Okay, well, maybe Amer, you could comment on those then.
Yeah. So this is our really vision for the future, to have a version of NEXUS to be accessible over the web using cloud services. I'm not really able to speak about the details of all of that. It's still something in our plans. We haven't started executing that, but this is something that we believe, and based on our some interactions with practitioners in the industry, that having web services or providing simulation as a web service on the cloud, I think would be very beneficial. So that's the direction we're going to. I apologize.
Well, and also, I guess,
a lot more details.
I guess also the integration, sort of focus on the mesoscopic level, which is sort of in between the detailed micro and the macro levels. And actually, I don't know if the question about integration was related to the integration with the activity-based model. So we've had some study with Professor Miller's group to try to integrate NEXUS with their overall activity-based modeling system. So obviously, NEXUS really is a platform for simulating transit movements, both for passengers and vehicles. And this is a key input in any overall multimodal transportation planning system. So, modern or next generation activity-based, agent-based models would require a detailed model of the transit system. So we've been actually working with Professor Miller's group to integrate NEXUS within their bigger integrated land use transportation system. I get it. Good. Questions. If anybody has a question, they can either put in the chat, or they can also just raise their hand, and I'm trying to scroll through to keep up. There's one new message. Transit decision maker, which compose, which types of plan do you see most transit agencies perform versus their central ministries? I think that was a very nice slide you had of the strategic, tactical, operational. I'll let you answer, but I think most transit agencies have to do all of those, but they do them at different time frames, like you said. But maybe you can.
So as the slide really showed, that there is different levels of planning. There's the strategic planning, and this is done within the realms of the transit agency, but as well, of course, in collaboration with bigger organizations, like in our context here, the City of Toronto and Metrolinx. So strategic transit planning happens within this context. Shorter term planning, like tactical planning and operational planning, is really within the realm of the transit agency itself. So the tools and analytics that we are developing are really mostly trying to inform or help transit agencies with those transit tactical and operational planning tasks, scheduling, route design, and so on and so forth, and operational management, real-time management, and so on. So for those decision-making tasks, There's a lot of need really for advanced analytics that are computationally efficient and also provide useful and timely information. And utilizes really existing and diverse data sets. So that to a large extent has been the focus of the Transit Analytics Lab studies and research program. But we also have a number of studies also at the strategic planning level.
Yeah, I just add on, I guess with the part related to in ministries, it depends on the province a lot. I mean, in Ontario and Quebec and BC, the provinces play a prominent role in overall infrastructure planning. And so they, individual transit agencies have to fit their strategic plans within that framework that's established by senior levels of government. Other provinces, Saskatchewan, Manitoba, the ministries don't play any real role in transit. So it's really up to the transit agencies to carry the whole ball and then just negotiate for individuals subsidies for capital investments. There's a question there for Willem. Do you see it, Willem?
Yeah, does delay data include consist length? I believe the delay data does include train component makeups. Most of the data I used was similarly length trains, but no, I didn't look specifically into consist length, although it's likely I put that into the regression algorithms and it probably didn't consider that super important. But looking at specific connections, like is there a connection between consist length and specifically overshoots? That would be an interesting thing to dig into. So good question.
I don't see another question right now. I guess question about data availability to all of you in terms of these different simulation tools. Peter laid out very well the trade-offs, but does the mesoscopic really allow? There's available data that would allow it to be high performance for its intent.
Of course, the more data, the better. And we currently have some for the GOAT network. We currently have some the real-time train tracking data, and that is also we can also collect some of that ourselves as well for the network level data, and we also have some delays and dwell time data as well that we can use. And building the components about for the ladder structures, we can collect data ourselves by looking at actually just going there, going to Union Station and observe how the trains navigate through the ladder system, and think about ways of how to turn that or abstract that into a model or component, one component that captures the entire ladder, I guess logic as much as possible. But the data is sometimes it's hard to obtain, but the idea is that we'll use as much data as we have, and then with the simulator, we can get based on what we have, we can get useful results without having to needing all of really detailed data that is that's typically required for microscopic models.
Right. Good. Okay, maybe we're at time. I would like to thank all the presenters, and we have a 15-minute break, but strongly encourage everyone to come back. We're having two presentations on a totally different topic, but a pretty hot topic right now, which is the use of Wi-Fi traces for various analyses and in terms of origin, destination, and other analyses. So please come back at 10:55. Thank you.
Okay, hello everyone. So the next session will be a little bit shorter session on the use of Wi-Fi data in different applications in transit. We've been quite fortunate to sign a data sharing agreement with BAI Communications, which installs and manages the Wi-Fi infrastructure in the subway system. This data actually can provide a lot of insights on flows and flow patterns across the subway system, and also give us some indication of the performance, user experience, as well as subway performance. So we conducted a couple of studies on this, on the use of Wi-Fi data in a couple of applications that we are going to share today with you. So first presenter will be Aidan. Aidan is a fourth-year undergrad student at U of T in the engineering science program. He majors in aerospace engineering, but he was bitten by the transportation bug while on a work placement at IBI Group. So Aidan is conducting his fourth-year thesis on the use of Wi-Fi data to analyze user experience and subway performance, but he worked in the transit analytics lab last summer, and he's going to report on his work in that area. So Aidan, over to you.
Thanks so much. All right, let me just share this. All right. Super. Yeah, so thanks for the introduction. So today we'll be talking about the system performance of the TTC and some insights we can gain from using Wi-Fi connection data. Thanks as well to Willem, Natalie, who is an undergraduate thesis student last year, and then of course, Professor Shalaby. So to start, the TTC is a bit unique in the way that it has Wi-Fi available on all the station platforms on one network called T-Connect. Some of you might have connected to it if you've used the TTC before. However, our major phone carriers actually don't offer service in the subway, unlike in some other systems in other places. So you've maybe seen these kind of three lump looking things around the system. Those are actually wireless access points that are available both at the platform and the concourse level. So the way that we kind of sort of see a device journey happening through the system, devices will check in if they've registered with a T-Connect network before, even if they're not connected to the internet. We'll see them arrive at an entrance access point. A passenger might travel down to that device to a concourse access point, and then they might go to a platform, at which point they might wait for a train, and then join a train and then leave that access point. So we kind of see these associations and dissociations as the key metric throughout this. We can sort of build together a journey profile. Obviously, given the lack of connectivity in the subway tunnels, we don't necessarily see a user's journey precisely as they're going through the tunnels, but we can infer this from arriving at and leaving stations en route. So this sort of second diagram here shows the different patterns. So a through device, for example, might associate at a previous station, so at Bathurst, say, then travel to Spadina, associate again, and then associate in St. George again. And we can say, okay, well, clearly that device is traveling through. There's some timeouts on here as well. But within a certain time frame, if we see that through pattern, okay, well, that device is attached to that person, must have traveled through. Likewise, arriving and departing devices, whether that's sort of the first point of entry or the last point we see them for a given time frame, we say, okay, well, the device must have left the station platform and headed up to the concourse and then kind of continued on wherever that user was going. So there's really a lot of possibilities with this data. One of the fun things last summer was to kind of just explore and conceptualize and see where we could take it. So the first things we looked at were sort of these two different silos of explorations that require train location information and those that don't require train location information. So the first one was looking at headway regularity, and this is kind of an important thing. One of the hallmarks of urban transit, especially rail, is that it's not there should be reliable headways. It should be frequent. You sort of should be able to arrive at the platform and not have to wait all that long. So we wanted to see the TTC has service standards, but what are they kind of performing to? and look at that really from a passenger viewpoint rather than a train recording viewpoint. And then likewise, also looking at for the platform wait time and the origin destination regularity. So what is that user experience like? How long are people waiting throughout the day, throughout different parts of the network? And how reliably can you get to your destination? If you think that you have a 35-minute trip, is that pretty much always on 35 minutes? Or are we seeing these sort of wild swings based on performance characteristics that maybe vary across the network? And we'll get into this in just a moment. So just for anyone who is not maybe familiar with the TTC network, it's a pretty minimum spanning network, as I've called it. We've really focused here on line 1 and line 2 for our analysis. This is obviously complemented by a network of suburban buses to kind of increase access beyond the subway network. We do envision that in some other use cases and other systems, this kind of Wi-Fi based analysis could actually be used to look at passenger routing and sort of route choice. But in the nature of the TTC's network, there are very few places where that route choice would sort of be evident through this data, since there's just not usually more than one logical way to go. So diving first into wait time estimation, this was kind of one of the first tasks, and we wanted to look at, what do the waiting times look like on platforms throughout the day? So this is kind of focusing on the AM rush, which is one of the more traditionally studied periods. And what you're looking at here is actually density estimates of platform wait time in minutes, sort of looking at all the passengers for a 2-hour AM rush period on line 2 last year. And you can see that, generally it's pretty consistent as sort of a lumped distribution in the, 0 to 3 minutes in most cases. And this kind of reflects what we'd expect. Most users are able to arrive, wait a couple minutes, get on a train, move on. However, there are sort of this tail end, which represents that likely throughout that 2-hour period, there was a few times where headways were increased, and an increased number of passengers were waiting on the platform for that. So just sort of showing that distribution. We envision this could also be useful of, investigating, for example, why does the station have an irregularity? Castle Frank here, we anticipate that that's partly just due to the nature of the Wi-Fi infrastructure at that station, since we did see a lot of very, very short associations there. But this is sort of an interesting starting place. This leads us into looking at sort of a different visualization of the same thing. So looking at the mean and the standard deviation of same. One interesting thing to note here is obviously Bloor-Young has a much longer mean device wait time throughout this AM rush. And we also kind of anticipate that's either from transfer passengers who are spending longer in the station, navigating from platform to platform, or also potentially passengers who may have been, walking down from the concourse, and that took a bit longer in that station setup. Another, sort of thing to point out here is generally, with the exception of the terminal stations on either end, we do see an increased standard deviation as we get to the center portion of the line. This reflects from our understanding the TTC's operational policy of sort of dispatching from a schedule at the end of the line. And, once you're at the center of the line, due to varying perhaps passenger boarding and alighting times or other operational conditions, that standard deviation does increase a little bit, and just the headways are slightly less regular. Moving on to sort of looking at the median platform wait times across the day. So what you're looking at here is really on the y-axis, a representation of the hours of the day. And then on the x-axis, really moving through the line. You can see pretty clearly in AM and PM rush periods, there is a lower median platform wait time. So that really does confirm that the TTC is scheduling an increased amount of service, and that is happening in reality in the AM and PM rush, and then that's slightly decreased in midday and decreases pretty significantly after 8 p.m. So those wait times increase, as you see with the darker colors. We didn't see a lot of variability across the line, at least in sort of the relevant sense. There is a little bit, but it's not major when you look at it kind of over the course of the day. So it doesn't indicate that certain stations are always having irregular headways. Likewise, on the weekends here is what we're looking at, and that shows a pretty similar service pattern throughout the day, with again a bit of a decrease towards the late evening. So the next kind of investigation we had was travel time variability. This was something that we really wanted to look at because we know that travel time variability is a big factor in kind of the user experience and perception of a transit journey. If you're not getting to your destination on time, and it's always, you're either early or you're late, that really can decrease the utility of a transit system in someone's mind. For starters, we classified trips both based on their number of transfers and based on their length. So you can kind of see here, pretty logical. And just to sort of explain this portion of our analysis, what we've done here is we've actually aggregated all devices that travel between a station pair in a given time period, and we calculate the coefficient of variation for that. So what you're going to be looking at here is based on station pairs, not based on individual devices. So we then classify each station pair into what its sort of category is. So for example, Museum to St. Andrew is a short journey without a transfer. And we're going to go ahead and plot those. So here we're seeing these density distributions actually of the coefficient of variation based on the type of journey. So as a reminder, the coefficient of variation is just a relative measure of the sort of standard deviation relative to the length of the trip. And so perhaps unsurprisingly, we can really confirm that short journeys with a transfer and just generally short journeys are far more variable relative to their overall journey time. And this is driven by both journey length and transfers, that variability. So a longer journey, even though it is longer, is actually generally more predictable and won't sort of leave you arriving at different times while departing at the same time. And it's just a comparison. We've also compared this to the GTFS feed with R5, showing that most of this variability is not scheduled. It is just from operational conditions. Likewise, we've also kind of taken this opportunity to pull this analysis out of just the AM rush period and look at it as well on Saturdays and other times throughout the day. And we did see consistently on Saturdays that there's actually a higher average coefficient of variation and generally a greater spread, which means that as the headways are reduced on the weekends, we see again less reliable journey times. And another interesting analysis we saw out of this was most journey pairs are actually quite a bit faster than predicted by the GTFS, but especially trips to the transfer. This is something we've gotten into a bit more, so I won't go completely into it here. Feel free to ask questions. But generally, we hypothesize that a lot of this is due to the nature of how transfers are calculated in GTFS and the fact that actually a number of users might be making transfers faster than expected. Regardless, we also, the GTFS is generally a fairly conservative estimate by our understanding, and one of the things we're still looking at is how exactly sort of platform access and egress time figures into this, because that is perhaps a couple of minutes that aren't necessarily accounted for. We're only really looking at users from their journey from sort of station to station, and I know some transit planners will also give a couple extra minute buffer for sort of station access and egress. Now we also looked at sort of a slightly different metric, the buffer time index, and that's defined as the extra sort of time you need to leave to be on time 95% of the time, so late 1 day per month, and that's just shown here. These violin plots again illustrate sort of a similar understanding from what we came to with the coefficient of variation, and generally that our shorter trips, and especially those with a transfer, have a higher buffer time index and are just going to be less predictable. So basically you do need to leave a greater buffer time relative to the journey itself, which suggests there's sort of a base amount of variability baked in when you access the transit system, and that's not really scaling quite to the same extent as you make a longer trip on the system. So our last kind of area of focus was subway arrival detection, and this is something we really wanted to again go back to this and look at how can we tell from users how trains are moving through the system. So this is kind of flipping the problem of how can we see what users are doing from trains on its head. And we were actually able to very successfully find, based on peaks sort of in the device association patterns with this particular station's Wi-Fi access points, when a train had arrived. And so this graph illustrates here kind of a net number of devices and actually looks at an hour at Sherburne Station. This was on an afternoon in August last year. And the convenient thing is we'd actually gone out and identified ground truth data. So I actually sat in the subway for about an hour at Sherburne and just recorded when trains arrived and left. And as you can see, it was a really actually very successful matching to those gray bars with the device association. So we can say this is quite a reliable method to sort of make those estimates of how trains are moving through the system. And you can also see here, this is actually a good example of the headway variability. This is just a normal afternoon, but you can see there's, at times almost 10-minute gaps between the trains, yet there's other times where there's only 90-second gaps. So there is a pretty significant headway variability, as we've seen in the wait time distributions and other analyses. So kind of, where next? And this is all I can share. This is sort of something I'm working on for my thesis project is how can we use this information to understand how disruptions and delays propagate across the networks. That is one of the sort of hardest things to model and measure in the fact that it's not sort of the network's normal operational conditions, and oftentimes it's it's kind of happening as it happens. But Wi-Fi data is a really good sort of method for understanding that. So for this, what we've done is sort of identified candidate delays. This is from the TTC Notices Twitter account, and we're looking at sort of various delay criteria. So what lines did affect? Was it in the central area of the network downtown where the shuttle bus is needed, et cetera? And so one preliminary analysis, this is still ongoing work, but looking at kind of how the waiting time can spike during a delay. And so as the trains stop running through the system, passengers are stuck on the platform, and those associations kind of stay. And so here is just kind of an example of how much the waiting time can spike, but also how you kind of see it spike with the stations and then eventually start to come down as trains run through again. At the same time, though, that waiting time doesn't continually go up as passengers perhaps leave the system, take an alternate mode of transport, etc. So more to come on here. This is still very much ongoing work. So just kind of to reiterate, I know we're almost out of time, but this has been an opportunity to really look at the passenger-based metrics rather than just relying on vehicles, getting actual travel times from Wi-Fi and cellular data, and really, sort of reimagining what analyzing reliability can look like. And then finally, also kind of connecting that back to the trains themselves with using people to identify where the trains are in the system. So that's all I have.
Thank you very much, Aidan. Indeed, very interesting. And one of the interesting points is that Wi-Fi data can actually enable us to start looking at user experience and analyze really person-based user experience as opposed to vehicle-based metrics that have been conventionally used. So that's a great piece of work. So our next presenter is Diego da Silva. So Diego has a PhD in computer science and is currently a postdoctoral fellow at the Transit Analytics Lab at U of T. And his research bridges between both public transit and cutting-edge computational methods to build better and more reliable mobility in cities. So he's going to tell us about a study that he also conducted in collaboration also with another PhD student, Firas El Said, on using Wi-Fi data to construct OD matrices across the subway network. Diego. You're muted, Diego. We can't hear you, Diego. Can you unmute yourself, please?
Check your check your source also. Sorry, that was me, Amer.
Oh, okay.
No, can't hear you.
Yeah. No, there seems to be some problem, Diego. We cannot hear you. So perhaps while Diego is trying to sort out the problem, maybe we can look at a couple of questions on the previous presentation.
Diego, you may want to just dial in with your phone if you are having trouble, just for audio's sake.
So Aidan, one question, which I believe Willem had commented on some of those questions, but I'll share them anyway for the benefit of everyone. So with regards to data coming from staff, station staff and loiters, how did you deal with that?
Yeah, so we generally, it's a good question. We generally have gone ahead and removed any devices that don't travel through the network. So, you do need to sort of have started at one station, associated another to be considered. So we anticipate that kind of removes staff that are just, at one station. Train crew, we've tried to avoid, what we've done is we can also see how many sort of device associations there have been through all time. So after a certain point, we also truncate that. So we kind of anticipate no one using the TTC for sort of commuting or personal purposes is going to be on there for like hours and hours a day. So we kind of have a limit. I think I'd have to look back at the code to see exactly what it's set at, but it's pretty high. I think it's maybe 3 hours. But we also anticipate that would probably remove a decent number of staff. When all is said and done, I think we don't think it's a huge part of the data. To be honest, I think it's a pretty small portion compared to everyone else on the network. And so for that reason, we've kind of, it's not been a huge concern, I guess I would say that.
Thank you. There's another question from Professor Saidi from University of Calgary about can longer wait time at Bloor-Young Station be also associated with denied boardings due to capacity limitation?
Yeah, we're guessing that's not the case just based on the time set that we're analyzing. A lot of what we've been looking at has been from 2022, where the system, ridership has returned, but we're not really seeing that 2019 experience of like denied southbound boardings in the morning peak. So I'd be hesitant to say that's sort of the main driving cause. I'm sure it's happened occasionally, but I think we also just need to look at that station geometry and knowing that it is kind of the main transit or transfer point. I think that a lot of those kind of longer wait times may actually just be associated with folks who have left one train from line 2, transferred over to line 1, and are sort of in that station for longer, and that's recorded as wait time.
Great. Let me just check if Diego has resolved the problem or not. Diego,
Hello?
are you with us? Yeah.
Can you
Okay.
hear me?
Perfect. Okay. Good. Okay. So yeah, we'll hold on questions maybe after Diego's presentation. So Diego, over to you.
Okay. Thank you. Sorry.
No problem.
Just 1 minute.
Okay.
Can you see my screen?
Yep. Looks good.
Yes, we can. Yeah. Go ahead.
Okay. Okay. Thank you very much. I'm sorry for this technical things. So thank you very much for the introduction, Professor. So today we will present the research for us, Amer and I have done over the last few months to estimate the origin destination matrix for the TTC subway system using Wi-Fi and AFC data. We divided our presentation into 5 parts. So there's a little bit of context, motivation, analytical framework, and results. Okay. We want to start defining an OD matrix and its importance in transport planning. So the OD matrix is a data structure that maps trips to each origin destination pair in a given region. So moreover, its primary application is to support engineers, urban planners, and transit policymakers in understanding demand distributions and patterns and eventually adjusting and improving the transit service. As we see on the slide, the only constraint for a balanced OD matrix is that the sum of trips in the columns is numerically equal to the rows, so the sum of the rows. So traditional approach to generating OD demand matrices rely mostly on household service, which are expensive in terms of resources and time. The availability of automated fare collection systems, or AFC, provides opportunities to overcome this challenge. But however, transit systems in many cities are tap-on or open systems only, in which passengers use smart cards only when they are boarding at the stations. As a result, determining the exact locations of a lighting station is not directly possible, making the demand analysis challenge as well. An alternative is Wi-Fi data, which we explored in this work, and we will detail in the following slides. Here in Canada, more precisely in GTA, we are lucky because we have had an excellent study running every 5 years since 1986. So the Transportation Tomorrow Survey is a laborious and expensive process and is the basis for long-term planning of transit modes in the region. In our research, the TTS served as a baseline comparison and validation of our results. Okay, some motivations and objectives. Our motivations and goals are to explore the potential benefit of user data collected through the Toronto subway Wi-Fi network, and mainly because of high data frequency and reliability that Wi-Fi data can provide. Despite being potentially applicable, the Wi-Fi data cannot be used directly, so to estimate the OD matrix, as it represents a fraction of the trips performed. So some pre-work needs to be done before its application. We developed a framework to generate an OD matrix based on Wi-Fi and AFC data. And to validate our work, we used the TTS 2016 as baseline. Okay, now I will explain a little bit of our analytical framework. So we split our framework into 4 steps. So the first step is the data collection. So we have their AFC and Wi-Fi data. So the second step is the data imputation, which we will detail next. Then the next step is the C matrix generation, and finally balancing the OD matrix. As we can see in the illustrated matrix that we have in the slide, so the AFC data compose the sum of the columns and rows in yellow. So because the AFC data represent the ground truth, so the true entries and exits in the system, while the trips will be used to estimate, will be estimated by the Wi-Fi data, so in red. I'll explain how we collected the data, so how the Wi-Fi data collection was done. So the primary purpose of Wi-Fi access is to provide internet service for passengers. Passengers who wish to use the free Wi-Fi service must connect and authenticate with the service provider. So this initial connection allows the mobile device or tablet to restore the provider's service set identifier, or SSID. After this initial connection, the device will always connect to the provider's access point, regardless of future authentication or active internet connection. Once the network SSID is stored, the device will associate with any AP once it comes within its range. When the device is associated with AP, a record is created by the provider in this case, the BAI, they would create this record, and then including the time of association, the AP, so the access point location, which is part of the router network, and the device MAC address, encrypted, of course. If a device loses connection, then a record of disassociation from that AP is created. The collected raw data of a single device are grouped into sessions. They call sessions, which are initialized by the presence of the device within the range of the Wi-Fi network, and terminated once the device has spent more than 15 consecutive minutes away from the network. So these sessions are then processed into journeys where the raw data is sorted by time. So the first station at which the device first appears is the origin station. And the last record is the destination station, which you are calling in our case, we are calling this Wi-Fi trips. The AFC gate count were requested for the TTC, which correspond to only the total entries and access of each station during a certain period. We use them to balance the OD matrix, and then we explain later the process. Unfortunately, not all APs can connect while the device is currently within the range. So the result is there are some gaps in the step-by-step location track. Because of it, we classify the trips collected by the Wi-Fi network into 3 steps or 3 types. Complete trips, when trips have a known origin and destination. Imputed trips, when we only know the origin or destination. And discarded trips, when we do not know the origin and destination. So we use a heuristic that investigated historical travel patterns to insert origin or destination data. So the window we used was 30 days. Yeah, because we are using data from 2021, when we know that the pattern, the behavior, the pattern in 2021 was changed because of COVID. So on this slide, we have 2 examples of trips. So the example 1 has a missing origin and is therefore a candidate for imputation. And example 2 is a candidate for discard because we don't have origin or destination, so it's more difficult to predict using the sample approach of imputation. Okay. Then we create the seed matrix and the initial state before running the balancing algorithm. So this is one of the most important part of our method. So the seed matrix is calculated from the trip distribution of the Wi-Fi data. So we obtain the absolute values of each origin destination pair, and then we calculate the percentage of trips to each destination. So for each OD pair, we got the proportion of trips. So this proportion approximates an impedance function for each origin. The matrix of trip percentage from the origin we call the seed matrix, as we see with the letter A. The AFC gate count is used to calculate the initial state of the imbalance matrix. So use the proportion, so the seed matrix, so the percentage of each trips on each OD pair, and then we multiply element-wise the vector containing the total trips per origin. Yeah, in this case, we are choosing origin, but it's arbitrary. We can balance starting from destination or origin. It doesn't matter. The result of this imputation or this multiplication that maintains the Wi-Fi percentage distribution is called the initial state matrix. So this, by the end of this process, we have the matrix C, And this matrix is, we call this imbalanced matrix. So these are the first stage that we will use to balance in the next step. Okay. Once we get the initial matrix, we are ready for the matrix balancing step. So in the literature, there are several methods, generally using impedance functions. As the initial matrix maintains the proportions of the trips from each origin, we look for a method to balance rows and columns simultaneously. We chose the growth factor doubly constraint algorithm for matrix balancing in this case. And the choice was made because it's an algorithm with a simple approach and fast convergence. The method calculates a vector of factors for rows and columns in each iteration until the sum approaches the values obtained by the AFC gate count. Just remember that in order to get a balanced matrix, we need that the sum of the rows and the sum of the columns, they need to be the same, or the difference needs to be approximately 0. Yeah, ideally 0. The exit criterion, as I said, is the constraint that the sum and the origin destination is the same. And by the end of this process, we have the balanced matrix. To validate our framework, we selected data from 5 business days in September 2021 in the morning peak. We used the TTS 2016 as baseline, morning peak as well. In addition, we divided the subway network into 10 regions with the travel attraction zone identified as region 1. So remember, it's the morning peak, and the region 1 is the attraction zone. It should be noted that in 2016, the year of publication of the last TTS, the stations in region 10, so up north, were not yet completed. Therefore, the demand estimated by the Wi-Fi data may differ from the TTS, as we see later. Okay, finally, the results. We created 2 methods, 2 models to be tested. So the first is with complete trips, that is trips that have a known origin destination. And the second model contains the data for complete trips and imputed trips. We call them as M1 and M2 respectively. For the data collection period, Wi-Fi trips corresponded to approximately 1/3 of the trips counted by the FC gate count. In the model M1, we have approximately 40% of trips via Wi-Fi, while the model 2, M2, has 75% approximately. So the total number of discarded trips was 26% of Wi-Fi trips. When we compare the models M1 and M2 to the TTS, we observe that the linear regression obtained are squared above 80% for both models, which is a very good result. In addition, the error is practically half in the model with imputed data, which means that the imputation heuristic reduced the dispersion of the data to the model M1 when you compare model 1 and a model 2. The coefficient of variation values is also consistent with the flow of trips to the morning peak, recollecting that the region 1 is the attraction zone. On the other hand, the counterflow is more challenging due to the scarcity of data in this direction for some regions. Consequently, we observed more significant variability in the counterflow regions. To check the geometric similarity of the matrices, we calculated the cosine similarity that measures the similarity between 2 vectors of an inner product space. In our case, as the values are positive, the cosine of similarity will vary between 0 and 1, and the closer to 1, the more similar the vectors are. As we can see in the table on the right, most vectors, both in column space and row space, are close to the number 1, which indicates high similarity between the matrices generated by the models and the TTS. As we explained in region 10, region 10 had the lowest indexes because most stations were not completed in 2016. However, excluding this detail, the result is promising. Another analysis we performed was to verify whether the expansion factor was stable of the day over the days of analysis. And both models had a stable expansion factor with a coefficient of variation below 4%. So the coefficient, the expansion factor is the comparison between the balanced matrix and the Wi-Fi data matrix. So when you compare, the idea is it possible to use some scalar and multiply this Wi-Fi trips that represents just a portion of trips, portion of the ground truth trips? Is it possible to multiply this number by some factor? And if this number is consistent or not? And then we can see throughout the days, we can see that the number is quite similar, which means that in this subset, it's possible to use the expansion factor. So all these patterns, they are really important because then we can build a more robust model. The extent of the analysis would be to verify similarities at the station level. Our preliminary results indicate that demand on the same line tends to be more similar than on different lines. So the fact of extracting this information pattern directly from the data can help us in the elaboration of more, as I said, robust models.
Diego, sorry to interrupt, but we are almost at time. So if you could please try to wrap up.
Yeah, okay. I have only those 2 slides. So in addition, just to conclude here, we have these similarities between neighbor stations, which is also good because we can extract this information as well to build robust models as well at the station level. So to conclude, the Wi-Fi based OD matrix showed patterns similar to the TTS, which makes them a reasonable proxy. Change in the travel pattern can explain the higher coefficient of variation values of passengers during the pandemic. Develop different trip imputation heuristics since more data implied a significant gain in the performance of the models. And the results show the possibility of generating OD matrices at finer time scales, for example, daily and at the station level as well, as long as we have AFC data available. So thank you very much. Thank you, BAI, for providing the data. So thank you very much.
Thank you, Diego, so much. Very interesting indeed. Yeah, as you highlighted, OD matrices are very critical, very important for various use cases and transit planning and operations. And a source like this one and the method that you developed would really be very helpful and useful to generate OD matrices at finer time scales and so on. So we have only a couple of minutes left, and I see that there has been a number of questions asked in the chat. So one of the questions was, can you use the Wi-Fi data to tease out, for example, commuters, like regular commuters versus those occasional users of public transit? So either Diego or Aidan, if they would like to comment on this.
Yeah, I think Aidan. So I can jump in. I think so. Yeah, the data set we have is well detailed, and actually we haven't explored all the potential of the columns that we have available for us. So right now we are just exploring the patterns, trying to understand how the demand is distributed, but of course, I think we can provide more detailed analysis.
So Diego, in explaining the imputation method, you said that you look at the history of the trips by the same device over the past 30 days. So could the methods that you use there for imputing missing trip details could also tell us something about, you know, the commuting pattern of a particular device?
Yeah, so just to explain, the imputation method that we chose was a sample method. So that's why we are just looking for the last 30 days. So of course, I think that we can increment the method with more robust features, and then use some other method to complement the demand pattern.
Aidan, do you have anything to add?
Yeah, I mean, I can say we definitely looked a little bit into the commuting pattern. I think the issue, as I think Willem might have mentioned, is it's a bit difficult to tell. You know, the MAC address isn't sort of forever on the system, so we do see these changeovers, and it's hard to get. You know, when we set it at a pretty high standard for reliability, like we want to see this person making the same trip at least like 15 or 18 times a month. Granted, this was also in 2022. It may be looking at it now with more folks returning to the office on, you know, that even more times a week schedule. Bottom line, it was a little hard to tease out. You know, we definitely saw repeat users, and we could often tell what a quote normal commute was, but it wasn't always enough different, I guess, from kind of like the infrequent users to sort of justify making broad claims in that sense. The other one was, yeah, we had we also were looking at not everyone who's using it once maybe associates to the Wi-Fi network in the first place. So there's kind of that bias too that we were looking at. So in the end, we didn't go too far on that analysis.
Okay, well, thank you very much. I apologize for not really entertaining the other questions because we're a little bit behind schedule. So again, thank you very much to both Aidan and Diego and all the collaborators on this project, and also to BAI for facilitating the data access. So with this, we conclude this session, and the next session will be moderated by Brendon. So Brendon,
I'm
over
here.
to you.
There was also just a lot of questions about the applicability of the methodologies for buses, and please look at the chat. There's Willem raised some questions, and there may be some ways of validating with APC data, but I think that's the next frontier to tackle. Can I ask Kenny Ling to turn on his computer and join me? There you are. Hi, Kenny.
Hi.
Yeah. Yes, so this this last session we wanted to add on sort of an open forum for discussion as TAL tries to identify new research directions. And so we've invited Kenny to provide some comments. Kenny has 20 years of experience in the public transit industry, spanning the domain of traffic engineering, simulation and modeling, service planning, business intelligence, and data analytics. He's worked for the Ministry of Transportation and the TTC before joining Metrolinx. He's now working for Metrolinx as a senior manager of LRT performance management, leading a team to deliver performance analytics functions for the upcoming Eglinton Crosstown LRT and Finch West LRT. So we were asking Kenny just to give a few thoughts, because he's been in the field for a long time. He's worked with some of the TAL folks. He's got sort of a knowledge about both the research side and the practitioner side. So we thought just to start the discussion, and then after that, we'll have an open discussion with everyone just to see if there are new directions that people can think of. So Kenny, why don't you give some thoughts?
Yep, absolutely. Thank you, Brendon. Thank you, Amer. So I'm also U of the alumni. Brendon and Amer was my professor as well. So I'm more than happy to share some thoughts, being as a transit practitioner in the past 20 years. So first of all, I just want to give a big round of applause to, Amer, Willem, Peter, Diego, and also Aidan. I think those are all excellent research. It really helps the transit industry, to, gain some further insights. In terms of some of the future directions, I think one thing that I want to comment on is about the pandemic. The pandemic definitely caused a great shift in terms of transit demand or traveling pattern. One thing that we find that on the Go Transit side is that we definitely see there's a shift in terms of traveling pattern. So we're seeing more weekend travel recovering quite a bit quicker than the weekday travel. So that's a kind of interesting finding. We find that over the weekend we recover maybe 70%, 80% of ridership, whereas when we look at weekday, we could be looking at 45% all the way up to 60%, depending on which corridor or which train rail line. So that's one thing we start to notice that after pandemic, and also especially because of the change of the working model. So right now with the more adoption rate of the working from home, we also notice that people are traveling slightly different in terms of between different weekdays of travel. So we tend to see that the variation of weekday travel, from Monday to Friday, it varies quite a bit more than before pandemic. So I think those two factors would definitely affect the people traveling within the region using transit, both in terms of the demand level, but also in terms of traveling pattern. So I think that would definitely affect how we plan our transit, and also how we operate our transit, and also in terms of research. I think that's one of the areas that transit agency would be really interested to find out how the pandemic really affects our way of traveling, our frequency of traveling, and also the way we make of public transit. Another factor is about safety. So on the Go Train side, during the past 12 months or so, we're seeing more and more of what we call transpassing event or safety event that really affect our operation. So that it causes many major delays along the the Go Train corridor. I think same for TDC. In the recent days, recent months, we're seeing more and more of this, all these safety events. So it really affects people's confidence in taking public transit. So it'll be interesting to find out that how this will really affect people deciding whether they will be taking public transit versus other modes of travel. So those are all, I think, play a pretty major role. And then I think the other thing is about with the transit expansion project going on, especially leading by Metrolinx. So we know that in the next 5 to 10 years, there'll be more LRT lines up and running. So the first one being the Ellington Crosstown LRT, and then the next one being the Finch West and the Ontario line and other rapid transit lines. So the major implications that with this rapid transit line opening, a public transit integration or transit connection will be ever more important, because we'll be seeing more and more better connection between Go Train line, TDC line, bus, streetcar, and subway. So it just becomes much more important than as a transit service provider, we provide this integrated seamless travel to all the travelers. So it's also important in the sense that how do we measure performance in terms of, are we providing the kind of connection that we were planning, that we're anticipating? So I think that's one of the areas that will be very interesting to find out, which is, I think, something like the NEXUS model, which would be an excellent framework, because that would actually help the industry to understand that, are we actually achieving what we want to do, which is provide an integrated transit system throughout the GTA that, allow people to go from mode to mode, kind of like in a seamless and integrated experience. And then I think one other thing I want to briefly touch on is about the way we measure performance. I know that a lot of transit agencies include Go Train, Go Bus, or TDC. Most of the metric we're focusing mostly is based on vehicle base. Just as rightly point out, I think in one of the research earlier this morning, I think there's more and more need of how do we derive some kind of performance metric that's truly reflecting customer experience, and not just based on vehicle. Are we delivering train on time? At the last stop, are we dispatching subway service at the beginning of stop every 2 minutes or so? But also at the same time, there should be better measured. How do we truly gauge the customer experience? Because at the end of the day, it's all about how do we deliver excellent customer service and also transit service so that people will choose transit over other modes of transportation. So those are just a few of my thoughts, based on what I've seen today and my experience in the last few years. Yeah.
That's excellent, Kenny. Yeah, it raises all sorts of interesting discussions. The measuring the performance, the customer experience, that's something I've always been thinking about for a long time. The Europeans developed a standard on the quality of public transport service 20 years ago that actually is an interesting circle where the kinds of KPIs that transit usually measures, which are vehicle-based, that the data of it is has been increasingly available for that through AVL, APCs, AFCs. But we're now getting to a point to measure the linkage of what is actually experienced by the customers, not just what is measured with the vehicles. And that, that is really what people react to. It's their perception of, of how they experience the system. And, the social media, we didn't talk about it because it's not really rail related, but there was a whole project that Amer and his team did on measuring, using deep learning for analyzing tweets, Twitter responses to get a better understanding of how the customers were perceiving the services and so forth. So I think that, and I think you're right. The whole NEXUS allows for integrating of different platforms, so we can start getting at things like, expected wait times, but expected wait times not just based on average headways, but based on, the stochastic nature of that and the reliability. And reliability is a real problem right now. Because of lack of drivers, operators, and lack of mechanics. The whole industry in North America is having terrible reliability problems, and this is before we recover ridership. I mean, we've got a little bit of flux here right now, but it could get worse. Security, safety, security. It's an issue. It's interesting to hear that even Metrolinx and Go there's been some sad incidents all over North America with security problems. And again, there's some reason to believe it has to do with outcomes of COVID and people's, increased anxiety and increased problems, mental issues that we're not very well equipped to answer with. And the changing patterns, again, that's a very good one, because the work from home, it's actually, I've been monitoring across North America. There's quite a bit of difference. I just heard the other day that, the MBTA's Boston's commuter rail is almost back to 100%, which is, it has to do a lot with the employers and how they're reacting to work from home. And in Europe, I understand, they're basically forcing everybody back. So it's that varies too. And then you mentioned about the expansion integration. And again, that's how we tie this all together through origin destination matrices, or the integration of different platforms. Those are all good. As before, you were, maybe describe a little bit, before you were in the current role in LRT, I think you were in a different division that was a little bit more directly related to the performance monitoring.
That is correct. So I was working for the Go Train and Go Bus team in operation performance. So the research that Willem has shown earlier, that's part of the data we share with U of T regarding delay data for Go Train operations. So my previous team was looking at the operational performance on the Go Train side of things, also Go Bus. So this is why that, especially in terms of how do we manage the day-to-day operation, we work very closely with we call the NOC team, which is a transit control center team, in terms of how do we manage our delay accordingly. So as you can see, the kind of delay that we're getting day in, day out, on the Go Train side of things there's a huge variety. And just like Willem has pointed out, the way we categorize it is a bit interesting. We have, different business unit who is responsible for mitigating different types of delay. And then the kind of delay we're seeing, that we also concerned about what we call primary delay or secondary delay. So, I mean, in a nutshell, we know that there's some delay that is causing subsequent delay. There's a cascading effect. So for instance, there's a transpassing event that will cascade into another train missing a time slot, so that it would be needing to wait for another train to pass through before they can go on. Or maybe there's a single tracking. So because of the transpassing event, it got delayed by 10 minutes, but then subsequently, because it missed the time slot, you have to wait for another 10 minutes before it can pass that single track location, because it is deviated from original schedule. So at the end of the day, so it's more also about how do we control the the occurrence of primary delay so that we can reduce all these subsequent secondary delay, and overall can improve the OTP on-time performance. Yeah, so I think one of the other topic I forgot to mention is about, I think there could be a need to analyze the relation between what we call primary delay versus secondary delay. So what kind of primary delay would generate a lot more secondary delay? So like some of the more safety related issues like transpassing, someone jumping the track, maybe some emergency event, maybe weather related event, those are the kind of delay that would cause a lot of resultant delay or secondary delay. It's just that we haven't done a lot of research into that area, and there's something that we know that we need to understand better so that we can come with some, preventative measure to control it better, making it better. Yeah.
And preventive measures, or might also be focus of capital expansion, where where you target trying to double track if you understand that that's the bottleneck or whatever. So another interesting aspect of this is we're really on a cusp of a very interesting period between the simulation tools, the deep learning, the expert systems. So far, we're still a lot of what we heard was, Amer had the three categories of descriptive, analytics. That's what Willem was talking about in terms of analyzing the causes, what's happening now. But then eventually that'll lead to predictive delay, and then eventually prescriptive, where one would actually have dashboards that assist the dispatchers, the supervisors, with the tools, with more optimization tools that can deal with with randomness and of the events. Any thoughts about that? Is that a correct perception? We're still primarily the descriptive part, and we need to move a little bit in the other new areas.
Yeah, that is correct. I think in terms of current state, within Metrolinx, I think we're still more on the stage of descriptive analytics. So we produce a lot of dashboard, KPI report that describe what is happening right now or in previous days or previous months. So we definitely have interest in seeing that what can we do about that in terms of some kind of predictive analytics. Like you said, maybe if we can inform the transit control team or NOC team, there's something that could be happening. Is there anything we can do in advance of doing that? I think the only thing is that in order for any transit agents to adopt that model, we definitely need to calibrate and verify, that, we maybe run in parallel. So you have a model that will be sitting within the transit control center or the NOC team that will be just used to compare. Does it actually telling us the situation, maybe, 60%, 70% of time, eventually help to increase the accuracy of it. But I can definitely see that there's something that, agency would be really interested in trying this out. But of course, with the participation of the actual business unit, something like the NOC team, they need to try it out to see that can we actually run it in parallel, and then building trust into using that kind of model. And then the last one, the prescriptive, I think we're still pretty in the infancy stage, so that will be like 2 steps down the road. But yeah, that would be ideal. Once we get to the stage of doing a little bit of predictive analytics, then prescriptive would definitely be the natural rate of progression. Yeah.
This is part of, all of this requires a focus on data. And the transit industry has been generally pretty conservative about investing in data, but I think we're getting to the point I'm seeing more and more job descriptions for data scientists, data engineers, business analysts, and these use cases. We're still at the descriptive part of the use cases and the dashboards, which are good for executive management, and that shows them, visualizes, and they can take that to their political masters to explain. But that's an investment, and it's a hard turn to justify, because it's not inexpensive. You have to get the people, the FTEs, you have to get the specialized expertise. And one of the thoughts out of all this thinking the TAL has been doing is Amer and Willem have developed a new graduate course in transit analytics, because we think that engineers now, they tended to focus more on the hard stuff, the concrete, the rails, the environmental analysis with building things. but we're now getting into, well, the future is really about data from my point of view, and it's getting into those different stages. And so that's why we're trying to move in the, in that direction. I'm just going to take a quick peek. I think I saw some new questions coming in. Question to Kenny: what is the extent of using simulation tools in service planning by rail agencies?
So on the GO Transit side, we have the service design department that has the open track that do rail simulation. So to my understanding is that even at this moment, they're still actively using open track to simulate different scenarios before they come up with the service schedule. So Wesley Su, who is the director of the service design team, his team has another business unit that is solely looking after rail simulation, like I said, using open track. So I know that they're doing a lot of active simulation, especially for on-call project or transit expansion project. So put it this way, it's just that for whatever service plan they're coming up with, they have to run it through the simulation model first, and then the planner would further fine-tune it based on the prevailing condition of the block period. Yeah, so my short answer is that yes, Metrolinx does use the rail simulation model open track. Yeah.
That's good. I'm not quite familiar whether how much simulation tools are used by other transit agencies or by CN and CP. I think I don't know. Willem, you worked for CP, I think you said. What's your perception? Oops, you're still muted. Oh well. I don't know. It's a good question, and it's sort of going on. Somebody asked me about the circle mobility. That's not the report. That report looks interesting. I just took a quick peek at it, but it's actually a European standard on the quality of public transport. There were two different standards, one on the framework and one specifically on the metrics. And I unfortunately don't have easily available to show this circle, but so far. Diego, you were answering about the sort of looking at demographic data. Yeah, that's always a question. We really would like to have more information about demographics, but there you get into the equation of privacy, and you have to be very cautious about anonymizing everything. But we really do need more understanding of it's not mass transit anymore. It's segments of customers, and they have different needs, different purposes, and different needs. And so somehow giving an overlay of demographics to the kinds of analysis would be very useful. Oh, sorry, Willem. Sorry, a question for you. They were asking about the use of simulation tools and Kenny mentioned about what's going on in Metrolinx, but I was just wondering if, based on your experience at CP, whether whether you feel that whether simulation tools are being used, or which ones. I guess that's mostly the open track, the micro ones.
Yeah, I didn't interact too much with the group outside of the operations center. We were in sort of a fireproof building. We didn't walk around all that much, but yeah, my understanding is there is a lot more detailed physics-based modeling. Open track is sort of European. There's one from Berkeley, I think, called RTC. Or RailSim, but there's a few detailed ones, and there's a lot of use of that in the freight world for measuring power, calculating how much power you need to do, or managing where your locomotives are located. So the sort of mesoscopic thing is not something I saw being used, but I can imagine it being useful from a customer service perspective to be able to be more sort of accurate in updating customers about where your freight is, things like that. So there is application there as well, but I haven't seen it used explicitly.
That sort of raises in my mind a question about, again, we need to move more towards integration, and that NEXUS and Spur or efforts in that on the purely rail side. But I was thinking about the LRT, where some of it will be on dedicated right-of-way and some will be in operation, or at least interacting with, in the middle of right of ways. That gets raised to the question of integration of the rail simulation with simulations for traffic, VISM, the TSP. How do you portray that? And is there much integration going on? Maybe Kenny, and I know Amer's done a lot of work on TSP as well. But what's your thought about that, Kenny?
Yeah. So I used to work for TDC for quite a long time when I was working as a shop engineer. So back at TDC, they do use VISM to do micro simulation, or especially modeling a transitional priority for streetcar and buses. So my understanding is that TDC is still actively making use of VISM model or micro simulation model to simulate the operation of TSP, especially with some of the advanced TSP algorithm. But I mean, I'm not too sure about this development. Haven't been in touch on that realm for a little bit. But my understanding is that, yeah, to your point, I think it's important that eventually there will be some sort of integration between the two modes. Yeah, so I do see that there's quite a bit of room for research or further development in that area. Yeah.
If I can add, maybe.
Yeah, please do.
Yeah, I mean, yeah, this is a very interesting topic, and I think I've had some conversations with people in the industry, and there's clearly a need for research in this area, because no single simulator that models, for example, the crosstown LRT, where parts is really automated operation and parts is, the train is interacting with the traffic. So VISM by itself or OpenTrack by itself cannot really do the job of simulating the entire corridor operations. And there is a need for a simulation platform that really combines those two. This is actually one of the use cases for NEXUS that we are thinking of, that we put together both OpenTrack and something like VISM, for example, or AIMSON, to model the entire operation of an automated LRT with some automation in mid segments, and also that has advanced TSP. So this is something that we plan in the next year or two to work on.
Mm-hmm. So I'd like to open it up more widely. Are there other questions, or does anybody have any thoughts that were stimulated by the presentations or that they've been working on themselves in terms of areas where TAL could focus a bit more? We've sort of talked about the general move towards moving from descriptive to predictive to prescriptive. And we talked about using Wi-Fi traces, and we talked about simulation tools and using AI and expert systems for the delay analyses. Are there any others that come to mind that people would like to chat? And also, you could, if you want to, actually, you can raise your hand and we can unmute you if there's anybody there. Well, people are pondering that. Amer or Willem or Diego, are there other thoughts of the rail related the discussions that have been happening in the chat room where here's one here: can traction energy be used in simulation? I don't know. Does anybody have any thoughts about that?
Generally, yeah. Well, Amer, you go ahead if you want, but generally, yes. For detailed simulations, if we're talking specifically about Spur, the stuff we've been working on, that's probably more into the physics side of things, and that's where things like OpenTrack is good for simulating.
And one thing I would like to add to that is that for the future coming LRT lines, Metrolinx will also be monitoring energy use. So there's specific clause in the project agreement that we will be measuring the energy use of LRT. Same for Finch West.
Yeah, we haven't actually done a lot on that front on the rail side. On the bus side, we've actually conducted recently a study to look at the energy or try to simulate the energy use and of battery electric buses. And really the impact of different real-time operating strategies, including TSP, on the discharge rate of battery electric buses. I think the capability is there, and we can use that also on the rail side simulation.
Is there somebody that I thought I saw something pop up? It's a little hard to scroll through the 60 people here. Yeah, in terms of sustainability, I guess that a lot of that it's sort of at the vehicle level or system level. I don't know if that lends itself also to analysis or to research that we should be carrying out. Most of the research I see tends to be, safety related or vehicle related or, track asset management related to track. We haven't talked about any of those very much. I don't know if anybody any thoughts about asset management and things of that sort. Kenny, I don't know if you've got any thoughts about the asset management side of things.
So asset management is one of the areas that we place a lot of focus on in the recent years. Because in terms of measuring performance, I think it's good that we measure customer performance. I mean, customer experience measure or maybe vehicle performance. But at the same time, as an asset owner, we have here heavy focus in terms of are we doing proper preventive maintenance to make sure that our asset would be delivering the kind of function expected, both in terms of fleet asset or infrastructure asset or stations. So even the oncoming, anything LLT and Finchwest LLT, we have very specific clause in terms of asking the maintainer to do a specific maintenance and make sure that they're doing up to standard. So it is becoming, like I said, one of the key focus in terms of asset management or asset management principle. How do we looking at costs from a life cycle perspective, making sure that we'll be delivering asset that in a life cycle perspective it be minimal and also efficient, minimal cost and efficient. And also the other thing is in terms of how do we hold our contractor or service provider accountable, because in the future LLT lines, it has a different model than before. So we have TDC running as an operator, but then we have a different maintainer, which is another company, we call it CTSM. So that is why it's important that we have specific requirement in terms of how do they maintain our asset according to the standard. Yeah.
There's a question here from Jeremy about how do any of us, the labs, transit operators, suppliers, improve or reduce the process of bringing findings into production? This gets at the core of trying to innovate in an industry that is risk averse has to be risk averse for political and public accountability rules. That opens up a whole range of things that in terms of government support for R&D and for pilot projects. I actually wrote a paper for ITS Canada looking at some of the experiments where some transit agencies have worked with academic institutions or with having unsolicited calls for unsolicited proposals on an annual basis to try to stimulate innovation and research. But it's challenging because procurement rules are fairly rigid and for reasons that we know. And it's hard to work with individual suppliers or with we found even individual with universities that's trying to work and through the maze of the mutual bureaucracies of both the university and the municipalities is often a challenge in its own right. But I don't know, Kenny, any thoughts about innovation that comes to mind?
So are you referring to the challenge that how do we bring into production, that question, or?
Yeah, how do we, I guess, the bringing it into production requires testing and innovation, and there's some universities are pretty well set up to stimulate research that can lead to innovation, but there's a middle period where you would have to test it and then first in pilots and then in semi-operational, and then how do we get to that point and how do we get transit agencies to actually participate?
I see. So my thinking is like this. I think in the past many transit agencies have pretty open-minded in terms of, let's say, TDC or Metrolinx, we many different departments wanted to try it out. I think one of the constraints would be that in terms of some of the assumptions, made by the research would be some of the major, could be a major roadblock in terms of whether the system is actually available to perform that kind of functions, or what would be readily available, in terms of data. So I think one of the things is that in order for any translation to truly adopt any kind of research model or research findings and then have it adopt into day-to-day operation, is that there needs to be a very a project build out to actually work with different business units to making sure that all of the assumptions of the constraint will be addressed fully before we can adopt that model. Because I think one thing is that I think a lot of great research that we find it interesting, but at the same time, there could be some kind of physical limitation in terms of, are we able to get that kind of data in the first place, or are we able to know the situation as specified in the research? That could be something that a project by itself to resolve. So something like the functional specification, are we able to address all of those? Would need to be addressed, and also in many cases, many of the functions, as mentioned in the research, could be encompass several departments. So let's say, just one, I'll give you one example here. So right now, we talk about a lot of integration of service between different modes, but then in reality, let's say a connection between TC train and TC GO train TC subway service. There's no one particular business unit that was solely looking after, are we doing a good job providing that connection? So in many cases, GO Transit will run its own service, TC run its own service. But then, I mean, in theory, service design department or service planning department will try to plan the service so that to minimize the waiting time. But in reality, we're lacking that body that is fully accountable for providing a true proper connection. So that is, it has to do with how your organization structure your business unit, and then what kind of accountability do they have. If there's no business unit being assigned that accountabilities, that function sometimes will be hard to follow through. Yeah.
It's a good point. As a previous life, I worked for the Canadian Urban Transit Association and was involved in innovation. As much as large transit organizations have more resources and more able to attract specialized expertise and have data available, medium-sized agencies often are more nimble. Can be, there's less departments involved, there's less people involved, there's less political focus, a high spotlight on them. So in many cases, they were where the innovations happened first because it was just easier. in some cases, yeah. I posted in the chat the paper, just short paper, 20 pages or so, about examples of places that were innovative. I want to just, if I can do this, share my screen just a second. Let's see if this comes up. Share. Can anybody see that?
Yeah.
Is it full screen? Is it full screen?
We see just your PowerPoint.
Yeah,
okay,
well, go to presentation mode.
Oh, sorry. Let me see if I can do this. Okay, here's the circle I was talking about, and there's the reference to the. There were 2 European standards.
Brendon,
sorry.
Just hit that swap displays button, and then we'll be able to see your full screen up at the top of your presenter view there, where the timer is.
So I say everyone. Sorry, no.
No, you're good.
Oh,
you'll just on your PowerPoint. If you go to where the timer's ticking up, hit that swap displays button.
Oh, I got you.
That will bring. Yeah, now we've got your full screen.
Okay, good.
Perfect.
So sorry, I got multiple things open here. But you can see there, that's the circle I was talking about, which was developed. So the first of these standards was in 2001, and the other one was 4 or 5 years later. But you can see this is exactly what Kenny and I were talking about, where the sort of vehicle-based technical KPIs are. This is typically what we measure here. But this is where what the users really are. That's what affects their behavior. And I think we're just getting to the point, 20 years later, where we can various tools are developed now. It's not just old market research tools of focus groups and so forth. We now can, revealed preference through the, social media or through, and analyzing, individuals through their Wi-Fi traces or so forth. So anyway, that's what I wanted to, what I was referencing. Okay, let me just stop that if I can. Stop share. Okay, there, we're back to normal, right? Has anybody, while I was doing that, are there any new questions?
I think there was a question
fares
about
as a quality metric. Oh, wait, here's someone.
Mm.
Has there been any thought into tools, use cases to model interactions between passenger and freight operations? Aha, to optimize capacity in shared corridors, something a very Canadian problem. Any thoughts from the researchers?
There was a previous question also on crowding analysis.
Okay, I probably missed that when I was maneuvering. Well, let's tackle the interactions first. I think the tools you're developing would be useful in that respect, wouldn't they?
Yeah. In fact, we conducted a couple of studies in which we looked at mixed traffic corridors using simulation and using also optimization methods. So this is definitely something of relevance to us here. And Spur is also being designed. Maybe Willem and Peter can talk to this a little bit more. That this is one of the use cases where we're targeting for Spur to analyze and also try to optimize mixed traffic operations and collaborative freight and passenger movements.
Sure.
Good.
Yeah, I do think that was one of the sort of use cases I envisioned for Spur when started putting the idea together. Sorry, my cat is hungry here. But it's relevant. I mean, Via Rail was just actually testifying at a committee this morning about the disruptions that happened over Christmas and talking a little bit about how the interactions between freight and passenger rail in Canada causes a lot of problems, and I know it's caused a lot of problems for Go Travel as well. So I think some more evidence-based analysis and simulation type analysis to support that kind of conversation is super important, and definitely something I was imagining with that kind of analysis, and maybe even to look at different policies of governance and see if that can change potentially how things work with mixed traffic.
Okay, good. And then I see the other question, Amer, that from Eve about comparing different mechanisms for analyzing crowding on platforms, whether it's video analytics as opposed to the Wi-Fi traces. Any thoughts about that?
Yeah, that's ideally speaking. Yeah, I mean that we would like to compare our results with video analytics. It's, as you probably can appreciate, getting and obtaining CCTV feeds are very hard for obvious security concerns, and that's something we've been trying to get in the past, but we never managed to get access to. So while I definitely think would encourage those researchers who can have access to CCTV feeds and using video analytics and compare them to other methods to really pursue this line of research. It would be great if agencies here in the call are interested in sharing their videos with us and applying some video analytics and comparing different methods of crowding analysis. We will be very excited to work on that.
I mean, video analytics have been much more commonly used in the sort of the roadside in terms of incident monitoring and management of freeways and so forth. But we've seen examples of suppliers that are starting to look at how these could be used first for collision with all the connected vehicle technology. There's more refined techniques for collision warnings and avoidance. And that might have an impact on LRTs in terms of, conflicts with turning vehicles, turning movements, but also bicycles and pedestrians. So I think that is a whole area we should think a little bit more about. It's been more on the road side, but not so much on the transit side. But I think there's something there to think about.
Yeah.
Yeah. Okay, I think we're getting to the end. I'd like to give Kenny, thank him first for participating and lots of good insights and a lot of good discussion. But any last thoughts, Kenny, that you want to say before I pass it over to Amer to wrap up?
Well, I'm just so happy to see, there's a lot of great research and really interesting findings. I think that, Metrolinx or TC, we can all benefit. So I think my only last word is that, as someone who is still practicing in the transit field in Metrolinx, we're still trying to continue to work, with U of T to see that what kind of support we can provide to them in terms of, let's say, data support. On the LT side, the same thing, when anything LT is up and running, we'll be getting a lot of different data, including like, CCTV, APC, SNTCS data, all those things. So yeah, looking forward to continue work with, the academia, academic community to see that how we can support each other. And then so that you guys can continue to produce this kind of, excellent research that will benefit the transit community.
Yeah, I appreciate that, Kenny. And we're always on the lookout for collaborators, and there's all sorts of different models, and we're more than willing to do a little dog and pony show for anybody who wants to find out what or delve into the more specific topics, or if there's anything where there might be mutual interest and potential collaboration. But with that, I'll pass it off to Amer.
Great. Well, thank you very much, Kenny, for your kind words and for sharing your thoughts and comments and insights about the future research needs. All the points that you shared with us, I think, very well taken, and we've taken notes of those, and hopefully we can contribute towards fitting those needs. And I would also like to extend our thanks to everyone who participated in this workshop. As I mentioned, and others have also mentioned, if you are interested in a particular study, we have publications on most of those studies, so we'd be happy to share those with you. And also, if you have any interest in any kind of collaboration or any ideas for future research, please feel free to contact us by email. We hope to see you again, perhaps like the next event will be the annual research day, which I mentioned will be sometime in the summer. We will announce widely the date, and hopefully we can reach out to all of you. Part of it will be related to rail transit research as well. So, and until then, so thank you again very much, and wish you all the best. Thank you. Bye.